Okay, ma'am.
So good evening to one and all present here. So warm welcome to third day online FDP program. Now the session will be started. Dr. Karthik sir. Karthik sir.
Yes, ma'am.
Sir, please
Yes, ma'am.
proceed, sir. Please
Good evening,
proceed,
ma'am.
sir. And good evening, sir.
Thank you. Welcome you all for the third day session on resilient infrastructure for cyclone-prone areas. We are privileged to have with us Dr. R. Ponudurai sir, a distinguished academician and a researcher in the field of civil engineering. Dr. Ponudurai sir serves as a faculty member in the Department of Civil Engineering at Tyagaraja College of Engineering, Madurai, Tamil Nadu, India. Throughout his illustrious career, Dr. Ponudurai sir have made a significant contribution in the field of structural engineering, particularly in the areas of fracture mechanics and seismic mitigation. His research have widely published in esteemed journals and conferences and proceedings. His dedication to advance our understanding of structural engineering resilience and disaster preparedness. Today, Dr. Ponudurai sir will give his insights on risk mitigation for earthquake disasters, a topic of paramount importance in enhancing the resilience of infrastructure in cyclone-prone regions. His extensive expertise and research in this area will undoubtedly provide us with the valuable perspective on designing and implementing strategies to mitigate the risk associated with the seismic events. Please join with me in extend warm welcome to Dr. R. Ponudurai sir. We welcome you, sir.
Thank you. Thank you.
So you can proceed now, sir. Please.
Okay.
Thank
Can
you.
you hear me? Everyone can hear me, I suppose.
Yes, sir. Yes, sir.
Okay. 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 Good evening, one all present here. I suppose total 66 participants are there. Okay, now, the topic given is risk mitigation and capacity enhancement in the earthquake disaster. So you might have come across this risk mitigation in terms of cyclone disaster. Now, in this session, we will talk about exclusively for earthquake disaster. Okay. Now, in the recent time, if you happen to see in India, so we come across so many disasters like earthquake, tsunami, cyclone, landslide, okay, flood. So these are so many disasters which cause so many lives of the people in our country actually. So we have actually preparedness program for all type of disaster. Even then, we keep losing the people. The main reason for losing the people during the disaster, for a natural disaster or any man-made disaster, is lack of preparedness and capacity. There is a lack in the capacity building in our society. Okay, so we will see one by one what are the potential deficiency exist in our society in RC buildings. So how to overcome that deficiency, particularly for earthquake disaster. Okay, because we cannot have the structure constructed for both earthquake and tsunami or cyclone. So we cannot have a single structure constructed for all type of disaster. So we have to keep on changing the design concept for various disaster. So in this case, we will be talking about it today. We will be covering what are the deficiency normally we do in our RC building, reinforced concrete building and masonry building. Okay, so that because earthquake doesn't kill the people, only the poor built structures are responsible for killing the people. That means you and me are responsible in this case. Okay, so we have to keep the points. What are the concept behind it to have the earthquake resistant type of design, or like a cyclone design of structure, or a tsunami resistant type of design. So we have to have a different kind of design for each disaster. Okay, so whenever we come across any disaster, we happen to see these terms called hazard or disaster. So the difference between hazard and disaster, we should know actually. What is mean by hazard? What do you mean by disaster? In this case, to explain the the difference between these two terms, we will have some analogy here. So here there is a hill. Okay, the stone is suspected to fall over this person now. He is standing underneath the hill. Okay, only a single stone is suspected to fall. The falling of the stone is termed as hazard. Okay, when we lose the people, when he loses the people, loses his life, then it turns to disaster now. So the earthquake happens at Chennai with a magnitude of suppose 7. The same earthquake happens in the Rajasthan in desert area. So what is the distinction we can make it? In case of Chennai, if you happen to see, we come across so much of life loss or magnitude of 7. But the same disaster, when the same thing happens in the Rajasthan desert area, so that time there is no life loss actually, but the same magnitude persists in both the cases. So in Rajasthan, we call it as a hazard. In Chennai, we call it as a disaster because we keep losing the people. So when we lose the people, it is called as a disaster. When we doesn't lose the people, that time it is called as hazard. Okay, that is the main difference between these two. So now it has become disaster now. So the falling of the stone from the hill cannot be prevented. Okay, so that is why the earthquake, tsunami, cyclone, landslide cannot be prevented. Okay, so the hazard that's what we call as hazard. But the hazard turns to disaster only when we lose the people. So that means now we will have to minimize the vulnerability or increase the capacity so that we can minimize the risk during the disaster, any type of disaster. Let it be cyclone or a tsunami or a landslide or flood, even earthquake. So we have to minimize the vulnerability or increase the capacity. Suppose the same person is under shelter, suppose we could have saved his life. Okay, so that is what we mean for capacity enhancement. So two things are possible. One is reduction of vulnerability. Suppose if the number of person is more than one, maybe 10 people are standing here, we are expecting 10 people to lose a life. So that vulnerability keeps on increasing means the risk also increases. So how can we minimize the risk is to reduce the vulnerability, number one, or we can have the structure, capacity building structures, so that we can minimize the life of the people. So reduction of vulnerability, increase in the capacity. There are two ways possible to minimize the risk. Okay. Now it has become disaster because he lost the life. Now we have two strategies here: mitigation and preparedness. Okay, so that we can safeguard the life of the people here. So the mitigation measures only the capacity building for this disaster. Okay, we have to increase the capacity for a building in terms of disaster resistant structure, like a tsunami resistant structure, cyclone resistant structure, earthquake resistant type of design. So that is what the mitigation strategies. But in case of preparedness, if somebody might have alerted him so that he can escape. Okay, so in case by doing preparedness also we can minimize the risk in the disaster. So there are number one is capacity building. That is what the mitigation strategy. Number two is preparedness. Okay. So look at this equation here. I suppose everybody can see this PPT.
Yes, sir.
Can you see?
Yes, sir.
okay.
Yes, sir. We are seeing, sir.
Okay. Okay. So this is a general equation now. The falling of the stone from the hill is called a hazard. Okay. So let us name it as some number. The falling of the stone, like earthquake also can be hazard. Tsunami can be hazard. Cyclone can be hazard. Flood can be hazard. So we can give some number 10. Okay. So only one person was standing there. So the risk is going to be 10. Okay. Now how to minimize the risk? How to minimize the risk? Here, instead of 10, I want to get 0. So what is possibility? Anybody? So you have to multiply so that the answer becomes 0. How it is possible? Can anybody can answer this question? How to bring the risk to 0? Yes? Anybody? Anyone? So we can, yes, we can reduce the vulnerability to 0. So that the answer becomes 0. So reduction of vulnerability or increase the capacity to 10. So reduction of vulnerability or enhancing the capacity can result the risk reduction. Is it okay now? There are two possibilities. Number one is to increase the capacity. That when we say increasing the capacity means we'll have to have a resistance type of structures like cyclone resistant structure, tsunami resistant structure, earthquake resistant structures. So by way of constructing the resistant structure, we can enhance the capacity. The vulnerability reduction can be also achieved. That means we can move the people from the out of the disaster zone area. Okay, so the vulnerability reduction is also possible. So there are two things are possible to minimize the risk. Number one is the reduction of the vulnerability. Number two is the capacity enhancement. Okay, so that is the reason we have the workshop here. So we are increasing the capacity. Is one of the capacity building measures, the FDP program for cyclone resistant type of building, so that the capacity is increased. We get the awareness among the people, so we can minimize the risk. Okay, so that is what the meaning actually. So the two things are possible. Number one is increasing the capacity. Number two is reduction of the vulnerability. So minimize that can minimize the risk during disaster. Okay. So in case of hazard, that is a potential threat to humans and their welfare. When we say hazard, it may be earthquake hazard or tsunami hazard or cyclone hazard. But for all the hazard, okay, we cannot stop the hazard, but we can minimize the risk now. That means losing the life of the people is possible. Preventing the losing the life of the people is possible. So when we say it's hazard, it is a potential threat to human. It may be earthquake, it may be tsunami, it may be cyclone, it may be landslide. But the hazard cannot be prevented. Okay. Now when we have the vulnerability, that is exposure to loss of life. When exposure to loss of life of the people. In that case, we can minimize the exposure. So in Chennai, the earthquake with magnitude of 7, that means the loss of life will be more there. So much of congested people will be residing there. And in the Rajasthan desert area, so loss of life will be minimum. So we can reduce the vulnerability, okay, or increase the capacity. So reduction of vulnerability or increase the capacity can minimize the risk. So when we say capacity, it is a usage of potential resources like capacity resistant type of structures. Okay? So probability of disaster occurrence risk. So how to minimize the risk? Either you can reduction of the vulnerability or increase the capacity. So the two things are possible. Okay, that is what this part of program is, the capacity building in a society. That is why FDP is being conducted on this topic. Okay, so assessment the disaster strikes. So immediately we respond to the disaster. So that is what the phase response phase. Then we take some time to reconstruction phase or rehabilitation measures. So earlier the government of India was spending more money on only the reconstruction and rehabilitation measures. But of late, the MHRD has taken over and they are concentrating more only on capacity building. Okay, so MHRD is concentrating more on capacity building because the amount allotted to disaster management is being spent by the government only to build the capacity. Okay, that is what the mitigation measures, the preparedness measures, and the prevention measures. So the entire fund is being allotted for prevention, mitigation, and the preparedness. Okay, but earlier to that, agriculture ministry was responsible. They used to give only the relief measures. They used to give the relief measures. Okay, now after it, the entire amount is being spent for capacity building. So when we increase the capacity, we can minimize the risk. So in case if you look at this animation, tsunami propagation. Okay, it has happened in Sumatra. Earthquake happened underneath the seabed in Indonesia. That resulted in the tsunami. Okay, so we lost almost 5 lakh people. Okay. So the reason being was the wave, the carried by the earthquake happens underneath the seabed was tsunami. Okay, that entire energy was converted to wave energy. That the wave energy hit the coastal line of our country. Okay, the people all around the coastal lines got affected. But the waves from Indonesia to our coastal region, it has taken almost only 300 minutes. Only 5 years duration. Okay, within 5 years, it is possible to vacate the people all along the seashore. But we could not do it because we did not have the awareness among us actually. So the 5 years is more than sufficient to vacate the people all around the seashore. Okay, but we know it is a tsunami because by knowing the wave, the amplitude and frequency of the wave, it is possible to calculate how much amount of energy the wave is carrying. Okay, it is possible. So in case if you take a photograph of the waves which are propagating there, okay, and the amplitude and the frequency, if we know, we can calculate the energy carried by the waves, and it can reach how long it can reach our seashore. That is also we can calculate. So everything was known to us. Only thing there is lack of implementation was the problem. Okay, so that is why the preparedness comes to the picture. So now our responsibility is to alert the people now well before the disaster, because we have here 5 hours duration. Within 5 hours, it is possible to vacate the people all along the seashore. Okay, now floating buoys are there everywhere. Okay, in the Indian Ocean. So the buoys keeps on sending the signal as and when tsunami occurs. So we will come to know much earlier. So now we can vacate the people all along the seashore. Okay. So that is what the hazard, we know about hazard now. We know about disaster, and there is a common link between the hazard and disaster here. Okay. So that is what we can say it's a risk now. We should be able to minimize the risk. Okay, how to minimize the risk is only a question now. To minimize the risk, you have to reduce the vulnerability. The circle should be very less, okay, small. Reduce the vulnerability so that we can minimize the risk. Is it okay? Madam, is it okay now?
Yes, sir. Yes, sir.
Okay, okay.
Please, sir.
So now our concern is to reduce the vulnerability. So to minimize the risk, you have to reduce the vulnerability. Okay. That means the number of people residing at a point, at a region, should not be more. So we can minimize the risk accordingly. So that is with the town planning authority in our government. Okay. So if you happen to this table now, it is a global occurrence of earthquake happened over the years actually. So the earthquake with the magnitude 8 and more, that happens only once in a year actually. Throughout the world. Okay, between 7 to 8, it happens almost this many numbers, 80 numbers of earthquake happens between the 7 to 8. Okay, between 6 to 7, it is 120. 5 to 6, it is almost 800 times 800 earthquakes happen. So if you happen to see less than 3, actually 8,000 per day. Actually now also earthquakes happens actually. The shaking of the earth happens now also. But only thing we are not able to perceive. Okay, so more than 3, if you go, then only we will be able to perceive the earthquake actually. So if you happen to see the between 7 to 6, okay, this is what amount of energy released during earthquake. If you happen to see if we divide this number, so we will get approximately 30 times. So 6 to 70 divided by 199, so approximately 30 now. So 199 divided by 6 is approximately 30. So that means only increasing one number in the magnitude will cause the destruction by 30 times. Okay, it is not that merely only 3.9 or 4.2. So we cannot take lightly that number is very less. So energy release also will be less more. It is almost 30 times more between one number. Increasing one number in the scale will cause amount of the damage intensity is almost 30 times. Okay, so that's what the importance of this table now. Now look at this table. This happens. This is the table which shows the earthquake happens in our country up to 2001 only it is there, but after that so many earthquakes happened now. If you look at the table, we can see some common point here. Down south Tamil Nadu, we have only one Coimbatore here. Okay. Any other point from the table? What we can take from this table? Anybody? So when we look at this table, we see Coimbatore. Okay, that has happened. Earthquake happened 8th February 1900 actually. Okay, so other than that, we cannot see any south district, southern district. Okay, so everywhere it happens only northeast actually. Assam, Gangra, Bihar, Nepal, again Assam, Anjar. Okay, Uttarkasi, Killari, Chamoli. So these are the places. The earthquake frequency is more here. Why it is more? Anybody? Can anyone judge why the frequency of earthquakes are more in this region? Yes.
Due to the soil strata, sir.
Due to the soil strata. Okay. Now actually we will get the answer in subsequent slides. Okay. Why only the north east portions are highly affected by the earthquake, the landslide sort of things. Okay, we will see that. So these are all the content actually I want to deliver. Okay. So when we talk about it, you might have heard a lot of lectures on cyclone. So regarding earthquake, we can say what is the reason for earthquake? Why at all we are building, which is constructed with pumping a lot of money, is getting damaged during earthquake. We will see that one by one. When we look at the causes of earthquake, okay, to understand the causes, first we should know the differences in potential. Suppose I have two water tanks, okay, kept at the same level. I am connecting these two water tank by pipeline. So both the tanks are having water. Will there be any flow of water in the pipeline? Okay. Can anybody give the answer? If both the water tanks are filled with water, will there be any flow of water in the pipeline?
No, sir.
No. Okay.
There won't be any flow.
Yeah, there won't be any flow. Okay, very good. Suppose if the water tanks are kept at a different level, now the water flows from higher level to lower level. Okay. So the flow of water takes place because of the difference in the head now. Same way, in case if you take a piece of wire, I have a potential here, 10 voltage. Okay, voltage, if you say 10 voltage, 10 coulombs of charge potential. When we keep the potential at this particular point, again 10, there won't be any flow of current here. So instead of 10, going for 100 voltage, 100 coulombs of charge, you can say. So the difference in the potential causes the current flow, electron flow. The electron flow causes the current. So the current flow takes place because of the potential difference between these 2 points. So whenever there is a potential difference, then only the current flow takes place. Same way, when we look at the structure of Earth, okay, so we have a core inside the Earth crust, inside the Earth, okay, where the highly density particle, heavy particle, high density particle, heavy particles are deposited. That portion we call it as a core. Okay, high density particle, heavy particles, like a nickel iron pieces. So during the formation of Earth itself, the high density particle got deposited at the core. Okay, and the lightweight particle rose to the surface. So that's what we say it's a crust. This is what we call as a crust. Okay, this we call as a core. So what happened is because of the difference in temperature between the core and the crust, because of the difference in density between the core and the crust, because of the difference in pressure between the core and crust, there is a potential difference. There is an electron flow takes place in between core and crust. So that current we call as a convection current. Okay. So if you happen to see this picture, the temperature at the core is approximately 2500 degrees centigrade. But at the crust, at the surface of Earth crust, it is only 25 degree to 40 degrees centigrade. Same way, if we look at the pressure, this is 4 million atmosphere at the core. But in case if you look at the pressure at Earth crust, it is only 1 kg per centimeter square. Okay, and the same way in case of density also. So density difference, because of the difference in the temperature and pressure density, there will be a current flow takes place in between the mantle region. Okay, that current flow takes place because of the difference. The current takes place because of the uh, pressure difference, temperature difference, and density difference between the core and crust. This current makes this mantle region to move clockwise or anti-clockwise. They are in semi-solid state. Okay, is it okay now? So this is what we say is a convection current. So if the current makes this mantle to move here and there, that is to and from motion. But what happened is the crust, which is just floating over the mantle, okay, they may collide each other. They may have the collision with each other. So that's where the earthquake happens actually. The plates which are floating over the mantle region is also expected to move. Okay, so that is where the collision takes place. The collision causes the earthquake actually. So that's what we say tectonic plates movement. You might have seen, okay, plate tectonics. So we have 7 major earth plates. Okay, 7 major plates in all around the earth crust actually. So this major crust, the plates are moving because the mantle is moving underneath the plates. The mantle is moving because of the current developed. The current is developed because of the pressure difference, density difference, and temperature difference between the core and the crust. Okay, so the core, the plates are expected to move. When it is moving, it is causing the collision at all along the boundary. So that's what happens here. So when we look at this table, we have a 7 major plate, like Eurasian plate, Indo-Australian plate, a Pacific plate, North American plate, South American plate, and African plate, and Atlantic plate. So these major 7 plates are floating in the mantle region. The plates are floating. Why? Because the mantle is moving. Why mantle is moving? Because of the current developed. Current, how it is developed? Because of the difference in temperature, density, pressure between the core and crust. So the plates are expected to move always. So that means whenever the plates are moving, it is going to have the collision all along the boundary. So the boundaries are more vulnerable. Okay, now if you look at these plates, Indo-Australian plate and Eurasian plate, okay, both the plates are moving towards each other. So when it moves towards each other, what happens? This is the region where Himalaya belt is available. Okay, so one plate goes one on another. Suppose this is an Indo-Australian plate, the Eurasian plate also is moving. Okay, it moves over one more region. Okay, this is the Indo-Australian plate, this is Eurasian plate. So that makes the hill formation. So I will draw exactly actually approximately. So we may have a plate of this kind. So this plate may be Indo-Australian plate. Okay, one more plate which is coming from other side. This may be of Eurasian plate. So these plates are moving each other. When it moves each other, the hill formation takes place. So that is how the Himalaya formation took place. The area there was a river was flowing there. So whenever the movement of these plates takes place, okay, the collision occurs. So the collision causes earthquake. Okay, when we say earthquake, it is nothing but a shaking of the earth. Okay, so total we have 7 major plates. Each plates are moving at 1 centimeter to 13 centimeter per year. Okay, so that is why you might have seen in the newspaper also, the height of the Himalaya keeps on increasing. The reason is the 2 plates are moving towards each other, so that the height keeps on increasing. Okay, so that is the reason. So that always happens actually. So that is why these regions are vulnerable region. Always the earthquakes are expected to happen. So in these places, we should have the earthquake resistant type of structure. Okay, so that means these areas are vulnerable. The boundary of the plates are more vulnerable. All along the boundaries, so it is more vulnerable. So always earthquakes are likely to happen in the boundaries, plate boundary. So in this region, we are supposed to have earthquake resistant type of structures. Okay, so that is what I was telling. So this is what we say convergent boundary. The Indo-ASEAN plate, this Eurasian plate. So moves towards each other, causes the hill formation. Okay. When the plates are moving away from each other, we have the valley formation. Okay. Valley formation takes place when the plates are moving away from each other. When we say the transform boundary, it is like a sharing action. The plates are moving the same plane, but in sharing action. That is we call it a transform boundary. So this we call it a convergent boundary. This is a divergent boundary, transform boundary. These things can happen all along the plate. That's what we call it as a tectonic plates. Okay. So that means this boundary of the plates are vulnerable. Always the boundary of the plates are vulnerable. So this all along the boundary, we want to have the structure constructed for earthquake resistant. So here we have the Himalayan belt. So that is why down south India, we don't face any earthquake in the recent times. So always happens only at the boundaries. Okay. Is it clear now?
Yes, sir.
Yes, sir.
Is it clear? Okay. So that is also one of the reason. One of the reason was moving of the plate. Okay. The plates moves towards each other. That is why the hill formation takes place. During the movement, the vibration occurs. The vibration only causes the waves. Okay. Wave propagation. Okay. So that is one of the reason of the earthquake. But one more reason, if you happen to see, in case of earth crust, we have the number of layers of the rock. Okay. You may have limestone here. We may have the granite here. Okay. We may have some other stones here. But what happens is, whenever we have the number of layers of the rock, okay, the layer in which the elastic modulus is very low, okay, they are likely to get damaged. Actually, since granite has the elastic modulus more, limestone is elastic modulus very less, so they are weaker area. Actually, weaker area. So all along the weaker area, so this layer the rock is expected to get ruptured. The point where the rupture of rock is taking place, that's what we call as a focus. Okay, the point where the disturbance happens underneath the earth crust is called as a focus. Okay, so when the disturbance occurs, actually what happens is the energy is entirely released during earthquake. In this layer. Suppose if you take if you take a piece of wire, I apply a tension in the piece of wire. Okay, the length of the wire keeps on increasing. Length of the wire keeps on increasing. There is a change in the length. The change in length by original length will result in strain. Strain multiplied by Young's modulus of the wire results in stresses. Okay, the stresses and the strain is stored as the energy in the wire. Yes or no? So that is what we call as elastic strain energy. We can calculate how much amount of elastic strain energy by looking at the graph. The area of the graph multiplied by the volume of the wire will give the amount of energy stored in the wire. Yes or no? Yes?
Of course, sir.
Yes. That's what amount of. Suppose if the energy exceeds the elastic strain energy, which is from the graph obtained, then the wire is expected to break. The same thing happens here also. The same thing happens here. When we have the structure constructed at the crust, so many structures are constructed. So if we have more weight is more here in this area, but we have the weaker rock here, that is limestone here. Okay, so the rupture is expected to happen at the limestone rock. Why? Because they are weak comparatively. Granite compared to granite, they are weak. Now the energy gets built up in the limestone because of the loads over a period of time. Okay, over a period, if you draw load versus the displacement, P versus delta of the load means when I say load, it is just above the focus point. The entire weight of the structure or a weight of the soil just above the focus point. So that the P is the weight and the delta is the displacement or rupture takes place. So if you happen to draw a graph, it will be P versus delta. So at this, the area under the graph multiplied by the volume of the material just above the focus point will give the amount of energy released during this earthquake. That means the limestone is expected to break when we exceed this energy. Okay, the stored energy. Limestone is having the capacity, some limit only. Okay, energy carrying capacity of the limestone is very big. If the energy stored in the limestone, if it is more than that of capacity, it is going to have the rupture. Okay, so the rupture, the point where the rupture takes place, we say it is a focus point. Okay, but your structure, which is constructed away from the focus point, is also get damaged. Why? What is the reason here? The reason is at the focus point, whenever there is a vibration happens in a solid medium, it induces a wave. Okay, the waves gets introduced because of the vibration. Whenever there is a vibration happens in a solid medium, it induces a wave. That wave will propagate in the entire Earth globe. Okay, entire Earth globe it goes actually. So that is why we could sense a wave propagation. Okay, earthquake is happening in Japan. We can measure the earthquake sitting at Madurai or Chennai, wherever it is possible, because the wave period is noting the time of earthquake and the arrival of wave. So from that we can calculate the magnitude of earthquake. Okay, how much amount of energy it is. So at the focus point, the body waves, primary waves and the secondary waves are introduced. Body waves. That is what the P waves and S wave. That the P waves and S wave will travel entire Earth globe. Okay, but that the P waves and S waves, it is not expected to damage all the buildings in the crust. Okay, the one more wave is responsible. We will see that what is that wave. The P waves and S wave, when it comes out of the surface at the epicenter, the surface waves are generated. Okay, it is like throwing a stone in still water. There is a wave propagation in the water surface of the water. That type of surface waves are generated at the epicenter. That the wave propagates underneath your structure, makes the structures to move to and from motion and up and down motion. So that is a reason for the collapse of the building. Okay, so that means we have waves which are originated at the focus number one. That is we call as the body waves. We have the waves which is originated at the epicenter. That is we call as the surface waves. So the surface waves is a reason for the collapse of the building. We will see how to tackle the surface waves. Okay. So that is what we say. So this is what the seismogram. When we say seismogram, we are like to have this type of waveform. So here there is a vibration always happens near the crest. Suddenly we sense some arrival of waves. Okay, that is what the indication of the primary wave, arrival of primary wave. After sometimes what happens is the wave amplitude is getting increased, because that indicates arrival of secondary waves. Okay, after sometimes again the amplitude of waves gets increased. That indicates arrival of surface waves. Okay, so the primary wave comes first, the S wave comes next, the surface waves comes next after that. Okay, so from this only we are getting the knowledge regarding the magnitude. We will see how to calculate the magnitude of earthquake, how to measure the earthquake. Okay, so that's what I was talking about. We have a number of layers in the earth crust. Okay, so there that the lithosphere, that is 200 kilometers. So that's what the problem happens actually. Okay. So the point where the rupture of rock takes place, we call this focus. The point where the waves gets out of the surface is called epicenter. Okay. In focus point, we have the body waves are originated. In epicenter, we have the surface waves are originated. So once the dislocation takes place, so we can visualize this fault, okay, from outside also. So this is what the terms involved here. The focus point or hypocenter, where the rupture of rock takes place. Okay, this is the point where the P waves comes out of the surface at the epicenter. Okay, this is our building. Okay, this distance we call as epicenter distance. This distance we call as hypocenter distance. This is the depth, focal depth. Okay, these terms are involved in the seismology. Okay, these are all the equation which shows the velocity of the primary wave, velocity of the secondary wave, the time taken by the waves to come, and the difference in time period between the primary wave and the secondary wave is given here. So that is not required for you now. So to know the concept behind it. Let us compare the balloon filled with the air pressures, some of air pressure, and the lorry tire, which is also filled with the same amount of air pressure. Okay. When the bursting takes place, noise will be heard now. Okay. Which will have the more noise? Anybody can answer this question? Anyone can answer? But we are filling with the same amount of air pressure in balloon as well as in tire. Okay. But when the bursting takes place in the tire and as well as in the balloon, so which makes a louder noise? Yes,
Sir, balloon may make a louder noise.
louder. If a lorry tire, you might have heard the sound of lorry tire when it's bursting. Is it more or less? Why the balloon now? Why not tire?
The compression in the small thickness may make a external pressure, exposed pressure, sir. But in the tire, the thickness of the layer is much more comparing with the balloon. So
Okay.
it may get compressed, internal compress may be generated, so the noise will be get low.
More. You mean to say a tire will be making louder noise compared to balloon?
No, sir, it's a tire only, sir, answer.
It's a tire. Okay. Why it is tire actually? This
Sir,
concept is very much important to understand the magnitude of earthquake.
loud.
So,
Yes, sir.
but because I am filling with the same amount of air pressure, the air pressure is same. But when the bursting takes place, why the tire makes a lot of sound compared to balloon? That is what my question. Okay, when we to get the answer, let us compare this. The balloon and the tire. If you draw load versus deformation or stress versus strain between the balloon and the tire, so it will have a stiffness of this kind. Okay, load versus deformation or stress versus strain. And in case of a tire, it will have the steepness. Okay, it won't have the flattens. The area under the curve, if you calculate, which will have the more area actually? Is it a balloon? A balloon will have more elongation actually. Okay, so area will be obviously very less compared to tire. The steepness of the tire is more actually. The area multiplied by volume is the amount of energy stored in this tire and the balloon. Is it clear now? The area under the curve multiplied by the volume of the balloon will be the amount of energy released during the bursting. And the area under the curve multiplied by volume of the tire will be the amount of energy released during the bursting of the tire. So obviously this will be more because the volume of the tire is comparatively more because thickness is more. Okay, the volume of the tire is more compared to balloon. So volume multiplied by area under the curve will be more for the tire. So the energy which is stored already is going to be released. The energy can either be created nor destroyed. Okay, nor can be destroyed. So whatever the energy was stored in the tire is going to be released in the form of sound energy. So if the stored energy is more here, the sound energy also will be more. Okay, the stored energy is less here, the sound energy will be less. So that is what the concept here. The same thing happens in case of earthquake also. So the amount of energy stored in the crust actually, suppose this is a focus point. Okay, this is what the weight of the structure, weight of the soil. You have the structure constructed everywhere here. So the load versus deformation or stress versus strain. In case if we calculate the area under the curve multiplied by the volume of the material just above the focus point will be the amount of energy released during earthquake. So that amount of energy released during earthquake is what we call as a magnitude actually. We will see what is magnitude now. I suppose it's clear now. The causes of earthquake, when we discuss the causes of earthquake, there are two possibilities. Number one is the movement of the plates, tectonic plates. Okay, the tectonic plates movement takes place because of the mantle, which is underneath the plate, is moving. Mantle is moving because of the current development. The current is developed because of the difference in the pressure, temperature, density between the core and crust. Is it got? I got the point now. Why at all the plates are expected to move? The plates are expected to move because mantle underneath the plates are moving. The mantle is moving because the current is developed. The current, how come in the current developed? The current is developed because of the temperature difference, pressure difference, density difference between the core and the crust. Is it okay now? That is what the number one reason for earthquake. Number two reason is any disturbance happens underneath the earth crust. Okay, that results the release of energy. So that release of energy causes the earthquake actually. So underneath the earth crust somewhere here, release of energy because bursting of the rock takes place. That energy stored in the rock is getting released. So that is being converted to sound energy. So that is why all the energy is being utilized to break the internal rocks actually. Only a part of energy comes out of the surface, makes this much disaster. Just imagine the entire energy when it comes out, that means entire person will get disaster, entire country will get disaster, it will be affected. We are lucky enough to have only a part of energy comes out of the surface. So all the energy is being used to destroy the rocks inside the crust itself. Only a part of energy comes out of the surface. Is it clear now? So I suppose so far, I suppose it's clear to everybody. What is the cause of earthquake? What are the causes of earthquake? There are two possibilities only I told. Number one is movement of the plates. Number two is any disturbance happens underneath the earth crust. Okay? Shall we go further?
Yes,
Any
sir.
questions?
Yes,
Okay.
yes, sir.
Okay. So whenever the earthquake happens, the waves are generated. This is what the body waves. We call it the primary wave. So if you look at this picture animation, the dot, each and every dot goes in forward direction, comes back to occupy its original position. Okay. Each and every dot, if you look at any one dot at least. So the dot goes in forward direction, comes back to occupy its original position. That's what the primary wave. That's how the primary wave moves underneath your structure. Okay. There is a compression and a dilation. There is compression and dilation. So if you happen to look at this block, when the primary wave travels, it gets compressed then elongated. Okay. Just to see, look at the animation. So that the block dot will get compressed then dilated. That's what happens in the building also. Okay, your foundation. In your foundation sides are getting compressed then elongated. So this is what the primary wave animation, primary wave propagation, wave propagation. So in this case, your building is not getting affected actually. Only wave propagates underneath the structure in foundation, compression dilation takes place. But the building is not getting affected. But the building is getting affected when next cycle, that is a S wave, when the S wave propagates underneath the structure. First primary wave comes, next S wave. S wave is looking like this. So all the particles are moving in vertical plane. All the particles in the surface is moving in vertical plane. So it is like tying a rope in a wall just to give a jerk. So this is what S wave propagation. So each and every particle will be vibrating in vertical plane. So in this case, the building is getting lifted up and down. Okay. So that time the building is getting lifted up and comes down. So in this case also, there will be a vertical movement. Building is getting damaged, but not to that extent. So the primary wave and the secondary wave is not expected to damage the structure entirely. But when the primary wave and the secondary wave comes out of the focus point at the epicenter, the surface waves are generated. So that surface waves only causes the damage, more damage. So what type of this wave? Anybody? Is it a primary wave or a secondary wave? Yes? Is it a primary wave or secondary wave? Because each and a particle
Secondary,
is
sir.
vibrating.
Secondary, sir.
Secondary wave. Because each and every particle vibrating in the vertical plane. Okay, just imagine your structure constructed over that soil. So the building is vibrating in vertical plane actually. Okay, goes up and down. So when the AC propagates, you look at the diagonal, that dot. One of the diagonal increases, the other diagonal decreases. Okay, so these P waves and S waves are generated at the focus point that propagates in entire the globe. But the primary wave doesn't damage the building, and the S waves also to some extent they will not damage. But when the surface waves comes out of the epicenter, okay, that when it propagates under the structure, so that time makes the structures to move in the horizontal pressure, to and from motion, and up and down motion also. So that is what the dangerous one actually. So this is what one of the surface waves, Rayleigh waves, which got originated at the epicenter. Okay, you look at the dot, blue dot, how it is looking like. It is like a sea waves, like a sea waves. So your building will be lifted up in elliptical fashion. Just imagine your building will be moved in this fashion. It is not the vertical plane or horizontal plane. It is moving in elliptical fashion. So in this case, how can we protect the building from this wave? It is not just possible. Okay, we will see how solution for this. One of the waves, surface waves, when it travels or propagated under the structure, makes the building to move in elliptical fashion. So the next, this is a Rayleigh wave. Just imagine. Complete distortion takes place when the Rayleigh wave propagates. So one more surface waves is a love waves. It is like a snake moving in a soil, in a surface, horizontal plane. So the each and every particle will be vibrating in horizontal plane. These are also more dangerous. So the love waves and the Rayleigh waves are surface waves. Okay, the love waves and the Rayleigh waves are surface waves. So love waves vibrates in horizontal plane, whereas surface that Rayleigh waves moves the particle in elliptical fashion. Okay? So when the surface waves are propagating under the structure, the building is expected to collapse. Okay, so we have to tackle the surface waves. I suppose you can understand about the animation of the waves. Okay, now you look at the picture here. This photograph has been taken during an earthquake. So when we look at this picture, these all the buildings are expected to have the complete collapse. Okay, but these buildings are intact. These buildings are safe. So what can be the reason? Anyone? Yes, anybody? It's already 7 o'clock. We have to go fast. So can anyone guess what is the reason for the collapse of all this building? These buildings are safe. Yes. Here, the orientation of the building. The orientation of the building is the reason for the collapse. Suppose when the waves are propagating in this direction, if you have the building oriented perpendicular to the wave, okay, so in that case it is getting collapsed. The same buildings oriented in this fashion, and the wave propagates in this direction, it is safe. So we know the epicenter, we know where we are going to construct the building. So we have to orient the building in this direction, that direction. Then only the building can be saved. Is it okay? So the stiffness in this direction is more. Because if you take the moment of inertia for this particular rectangular section, okay, the portion which is having the direction of the wave will have the D. This is what the B here. So the moment of inertia for rectangular section is BD cubed divided by 12. Okay. So in this case, here the moment of inertia will be more because the D is more. Here the moment of inertia is less because D is less. So less moment of inertia results in less stiffness. Okay, K will be less. Here K will be more here. So stiffness is more here. The building is not expected to collapse. So the orientation of the building is much important in a earthquake resistant type of building. Okay, so you have to orient a building in such a way that the epicenter and the building should have the same direction. Okay. And next, when we talk about the measurement of earthquake, and we have now only 7 o'clock up to 7:30, I suppose. Okay, we can measure the earthquake by qualitatively and quantitatively. So when we measure the earthquake by quantitatively, we call it as a magnitude. When we measure the earthquake qualitatively, we call it as intensity of earthquake. Okay. So when we look at the difference between this magnitude and the intensity, we have the M grade of concrete, M15 or M20 grade of concrete. Okay, it is made up of a cube made up of M30, suppose M30. So when we have M30 grade of concrete, that means the compressive strength of the cube is put to have almost 30 Newton per mm square. So the 30 number comes here, that indicates that can relate to magnitude now. But the same cube can be calculated, the strength of the cube can be calculated by having a rebound AMR sort of things, ultrasonic testing. So in case of ultrasonic testing, if the velocity is more than 4 km per second, it is a good concrete. Okay, if it is between the 2 to 4, it is a moderate concrete. Less than 2 km per second, it is a poor concrete. So qualitatively, we are assessing the strength of the cube. Here, the quantitatively, we are assessing the strength of the cube by dissecting. So the quantitatively assessing the earthquake is called as a magnitude. Qualitatively assessing the damage in terms of damage, we call it as intensity. Okay. So earthquake measurement by using a quantitatively is called as a magnitude. Qualitatively, if we measure the earthquake, is called intensity. Okay. So that is what the Richter scale we say for magnitude. I will go some. Okay, a little bit faster. What do you mean by Richter scale? Why it is called as a Richter scale? Why we consider uniformly accept in the entire world the scale is because it gives the same result in the entire world. Here, the Richter scale is having 3 scales calibrated. Okay, 0 to some number 0, 5, 20, 30, 40, 60, likewise, and one more scale. It is at the center. That's what we call as a Richter scale. And a third scale is also numbered here. So when we have the waveform, so first primary wave comes, then next secondary wave comes. Okay, so after that the S wave will travel. So the time of arrival of primary wave, the time of arrival of secondary wave. If you know that, that is known to you now, because this seismogram, that is the paper, recorded paper is given to you. The P waves arrival and S wave arrival, the time difference between primary wave and S wave is marked here. This location. Okay, the time difference between the primary wave and the secondary wave is marked here. 1, 2, 3, 4, 5, like this. Same way, the amplitude of the secondary wave is marked in third scale. So when we join these 2 dots, it is going to intersect the center point. So that is what we say it's the Richter scale magnitude. So that gives amount of energy during earthquake indirectly. Okay, this is now in this case 5. It may be here. It is maybe 6.5 something. Okay, so this number indicates the amount of energy released during earthquake. So that is what we say Richter scale magnitude. So Richter scale magnitude obviously have 3 scales. One scale indicates. Okay, one scale indicates. In one scale, the difference between the primary wave and the secondary wave, time duration, it is marked here. The third scale is marked with the amplitude of the S wave, amplitude of the S wave. So let us take the amplitude of S wave is 20, and the time difference between primary wave and the secondary wave is here now. So if we join these 2 points, it is going to intersect at this point. So this is what the Richter scale magnitude, 3.5 here. Is it okay now? So the 3, 4, 5, 6 are Richter scale magnitude that indicates amount of energy released during earthquake. Okay, I will go. This is what we say Richter scale. So this is what the SP time. 2, 3, 4, 5, 6, like that. Primary wave and the secondary wave. Here the SP time is 24 seconds. So it is 24 is marked here. And the amplitude of the SY is 23 mm. It is marked in this third scale. When we join these two dot, it is going to intersect at the center scale. The center scale, it is intersects at the magnitude 5. Is it okay? Any question here regarding Richter scale? Shall we go further?
Yes, sir.
Yes, sir.
So this is what the instrument. We measure earthquake actually. The instrument is called a seismograph. The recorded paper is called a seismogram. Okay, don't get confused between these two. So these are recorded paper. We will skip this. Okay. So this is what the intensity of earthquake. So the 100-watt bulb. Okay, so 40-watt bulb. So that number indicates the amount of energy, amount of illuminating power. Okay, so that can be that we can relate to magnitude. Okay, the illumination power keeps on decreasing as the distance increases. Okay, so that means the earthquake happens at this particular point, epicenter. So maximum amount of energy is being released. Okay, as the distance increases, the intensity, damage intensity reduces. Okay, the damage intensity means the amount of extent of damage. Okay, the extent of damage will be more at the epicenter. The damage will be less at far distances. So the illuminating power keeps on decreasing as the distance increases. Okay, that we can relate a magnitude and intensity of this. So magnitude we can relate with the 100-watt. The intensity changes at every location. That is going to change. Whereas magnitude is not going to change. So magnitude of earthquake is not going to change. Whereas the intensity of earthquake will be changing at each and every places. Okay. So this is what the intensity scale actually. So the intensity scale MSK is 64 intensity scale. It gives this information 1 to 12. So when we say intensity number 1, so only deducted by instrument. It is not going to be deducted by the Ohm's law. Okay, the magnitude approximately is going to be between 1 and 2. But when we look at this intensity number 12, it is got a total destruction. So we can see the wave propagation all along the surface of the earth. And we can witness all the collapse of the building. All the building will get collapsed. So merely based on the extent of damage, they classified they measured the earthquake. That is what we call its intensity. In case of magnitude, we go for measurement of earthquake by magnitude that indicates amount of energy released during earthquake. Okay. So our country, of late, is having 4 zones. Earlier it was having 5 zones. Okay, 1, 2, 3, 4, 5. Now it is only 4. As per IS 1893 Part 1, 2002 and 2016 also. We have only 4 zones. Okay. The area which gets affected frequently is in this region. You know the reason. Okay. Here we have the Indo-Australian plate. Here we have the Indo-Australian plate. We have the Eurasian plate. So that both plates are moving towards each other. So that makes the earthquake always frequently happening in this region. Okay. So these are all the area where the boundaries are not there. So that is where earthquake is not happening at down south India. Sorry. So 60% of our country is under threat. That is seismic zone 3, 4, and 5. Okay. So next we will see some of the deficiency, how to not to construct a building. What are the deficiency available in our structures? Okay, number 1, when we look at the load path. Okay, so you can imagine here there is a person. Okay, why at all building collapses when the wave propagates under their structure? Okay, just imagine I am standing in the bus. All of a sudden, driver starts the bus. When the driver starts the bus, okay, my feet, which is touching the floor of the bus, goes along with the bus. But my upper body is not going to cooperate with my feet. My upper body is going to receive a force in opposite direction. I am going to fall. Okay. So when the feet goes in forward direction, because of the bus, along with the bus, my upper body is going to experience a force in opposite direction. So I am expected to fall backward. Okay. The same thing happens. Just to replace me with the building now. When the earthquake waves propagates, when the driver starts the bus, your foundation goes along with the bus. Your upper story is experiencing a force in opposite direction. That force is going to push your building in opposite direction. That force is F equal to ma. That is more when the mass at the upper story is more. Mass at the upper story is less, means the force received by the structure also will be less. Okay. Now, what is the reason for the failure now? We are not taking these forces in our design. We take only live load and dead load for our design of the structure element, like beams, columns, slabs, sort of things. But here is a force which are expected to come when the earthquake wave propagates under the structure. Okay. Your foundation goes along with the wave, but your upper story is going to expected to receive a force in opposite direction. So that is the problem. You are not taken this force in your design. Now it is under compulsion. You are supposed to take this force also in your design. So the IS 1893, the code abbreviation, IS 1893, okay, gives the information regarding the how much force are expected to be received by the structure during an earthquake. So we can calculate the forces, horizontal forces, when the earthquake wave propagates. Depends upon the type of building, how much force are expected. So to calculate the horizontal forces, we can make use of this code IS 1893, part 1, 2002 or 2016. Okay, number one problem. So the force we are not taken in our design, number one. Number two, suppose let us take the forces generated at the roof is 100 unit. Okay, the 100 unit cannot be transferred to the soil as 100. Suppose if we have a building, okay, if we have the building here, so there, suppose let us take 100 unit of loads are there at the top, 100 units of load. We have the beams and the columns to transfer the load. Okay, the load from the slab goes to the beam, from beam it goes to the column to the foundation to the soil as 100 unit of load. So that means no elements in the building is expected to withstand the load. All the elements are being designed to transfer the load. Actually, the beams and the columns or slabs are being utilized in the RC building to transfer the load, not to withstand the load. Okay, whatever the loads are available at the top, okay, your design should be such that the load transfer should be perfect. Suppose instead of 100, only 80 units of loads are going to the soil. That means the 20 units of the loads are used to create the crack. So used to destroy the building. Is it okay now? So that means the design should be perfect enough to transfer the whatever the external forces are available to the soil without any dissipation. Okay. So here it is not possible to transfer the horizontal forces to the soil. Okay. The 100 unit of load cannot be transferred to the soil as 100 unit. So that is why our buildings are getting collapsed. Okay. We are not able to transfer the load which are generated at the roof level to the soil without the dissipation. So if we have 100 unit of load at the rooftop, okay, the soil, we cannot transfer the load, okay, as 100. That is why the buildings are getting collapsed. So the number one point, what we failed to take is the horizontal force which are expected to takes place during earthquake. This force also to be taken for earthquake resistance of structure. Okay. So that is what I was telling about. Okay, when the wave propagates, the foundation goes along with the wave, but your upper story is expected to receive a force in opposite direction, mass time acceleration. Okay, if we have the more mass at the rooftop, we are expecting to receive more amount of force. Okay, number one problem. Number two, these forces were not taken in your design. These forces has to be transferred to the soil. We are not able to transfer. So that is why the buildings are getting collapsed. Okay, so that is why we introduce shear wall here. Okay, shear wall is ordinary concrete wall. So we introduce shear wall because we want to transfer the load to the soil without any dissipation. Okay, by through the shear wall. Okay. Okay. So that is why after it we have been such, we have so many resistant measures in the building itself. We have the braced frame, we have the shear wall design. So many earthquake resistant measures are there. So we can look at these measures one by one. So look at these structures here. Okay, the ground floor is missing now. Okay, number one, the load path. That means the load path. Whatever the external forces are available, loads are available, that has to be transferred to the soil without any dissipation. If you are not able to transfer, the buildings are expected to get damaged. Okay. Here, in case of earthquake, the horizontal forces are expected to act. The horizontal forces cannot be transferred to the soil without any dissipation. So that is why the problem comes. So if you are able to transfer the horizontal forces to the soil without any dissipation, your structure is safe for load path. Okay. Next, we will get into the soft story or big story area. Okay. This is a building. Normally, we witness in urban areas. Okay. RC building. Okay. This building, is it okay for earthquake resistant? Anybody? Anyone? Is it okay? These buildings are okay? Or it is giving any say deficient?
No, sir, it is not okay.
Why it is not okay? Suppose if you take a cantilever beam with a point load, a number of point load. Okay. Let us take a 2, 3, 4. So you can draw shear force diagram for this case. It will be 2 here, it will be 5 here, it will be 5 plus 4, 9 here. Is it okay now? 9, here 5, here it will be 2. Yes or no? So that means the
Yes.
maximum shear is at the support. Okay. Maximum shear is expected to develop at support. The same thing in the building also, just invert this cantilever. So we tend to have a number of point load in a cantilever fixed at the bottom. If we draw a shear force diagram, so it will be looking like this. So that's what we call as a base shear. So the shear accumulation will be maximum at the ground floor. Shear accumulation will be maximum at the ground floor. But when we say shear accumulation, what do you mean by shear? Anybody? Shear force. Because this is very much important. You should know what is the impact of the shear force. What is shear force actually? Anybody? Okay. So to understand that,
Same
unbalanced
force acting in the opposite
particle.
direction.
Opposite direction. Okay, very good. Suppose if I am giving a what is that? A broomstick. Okay, I have given a broomstick. I have given scissor also. I am asking to cut the broomstick. Is it possible to cut? Yes or no? I have given
Yes,
a
sir.
broomstick. Yes. So,
Yes.
but I am giving a condition that you will have to apply equal and opposite forces. Okay, suppose a 5 unit from the top, 5 unit from the bottom. Now the broomstick will get cut or not?
No, sir.
No. Why? Because
At
by
same,
virtue of yes.
if the forces are applied in the same point, then there will be equilibrium, sir. So
Equilibrium. Okay. Now the problem is the scissor. If you look at the geometry of scissor, it will be unsymmetric in fashion. Purposely, the scissor has been designed Okay, to create unbalanced forces. Suppose you cannot have a equal and opposite forces by using scissor, by virtue of its geometry. So that is why in case if you have a 15 here at the bottom, top only 5, the resultant is how much?
10, sir.
10. The 10 is called as a shear force. That is what unbalanced force at a section. The 10 unit of force is going to cut your broomstick. Okay, the same thing happens. So that means it is going to, the shear force means it is unbalanced force at a section. It may be horizontal or vertical. Okay, so the scissor is being designed to create unbalanced force. That is why we are using for cutting purpose. The same thing happens in the building also. The shear gets accumulated at the bottom always. The maximum shear is expected to happen only at the bottom. But here we have given open story. There is no resistance to shear here at the bottom. The building will get cut because of the shear. The columns will be cut, and the ground floor columns will be damaged during the earthquake. The building will comes down. Okay, so that means we should have the shear resistance at the ground floor. Let us assume that this is a shear force diagram. We should have shear resistance. Okay, more than that of shear stress developed. In that case, the building will be stronger. So the stiffness and the strength should be uniformly distributed all along the building. It should be uniform, or the shear strength should be more. So that is why the temple, church buildings not getting collapsed. Okay, because at the base we have the enough strength and stiffness to take care of this shear accumulation. Is it clear? So when we use a scissor, it is not geometric. So the purposely it is being given to create unbalanced force. Okay, so that is going to cut your ground floor column. So that is the reason the ground floor is missing here, because you are given open story at the ground floor. The accumulation of the shear is maximum at the ground floor, but there is no resistance to shear. The shear strength at the ground floor is very less. Why? Because you are given open for car parking. So that ground story is always expected to get damaged. Okay, so that is why number one deficient actually in a building. Ground story should not get opened up. So we should have the enough shear resistance. Then only the building can be safeguarded. Is it okay now? So the ground story should not be opened up. Open ground story should be avoided. Always you should have the stronger ground story. That means in terms of strength and stiffness, it should be. So always the failure is suspected only at the ground floor columns. Okay, the ground floor is missing here. So that is what the open story failure. We say it's open story failure. Okay, and we will see one by one. See this is what storage here demand. The capacity should be more. Okay, so but we have given open story here. So the accumulation of the shear will be maximum at the ground floor. So the accumulation of this shear is maximum at the ground floor. So the shear strength should be more at the ground floor. So that means the shear is expected to cut your ground floor column. So the building is expected to come down. Is it clear now? See, this type of buildings are more dangerous because the shear accumulation is maximum at the ground floor. But here we have given opening now. So this type of building should be avoided. Okay, so the ground open story should be avoided in case of earthquake. But the same building will be useful in case of flood. Okay, in case of tsunami, you should have the ground story open so that the wave can travel, water wave can travel through the building. We should not stop the water waves. So in case of tsunami resistant or a flood resistant. But in case of earthquake resistant, you should not have the open story at the ground floor. Is it okay?
Yes, sir.
Yes,
Okay.
Yes, sir.
Yes, sir.
So if we happen to see the ground floors are getting damaged always. If the earthquake happened to be 2 seconds, 3 seconds further, the entire building might have come down. So that is what regarding the soft story and weak story. So when we say soft story and weak story, the stiffness irregularity all along the height of the building should not be there. That we call as a soft story. In case if you have the strength irregularity all along the building, okay, height of the building, then that time it is called as a weak story. So between the floors, so if we happen to see floors in a building, the strength and stiffness should be uniform in all the building. Strength and stiffness should be uniform. If the lack of stiffness between the floor is, that means it is the failure is called as a soft story failure. Lack of strength between the floor results in weak story failure. Okay, stiffness and strength should be uniform. In case if you have opening at the ground floor, so here the stiffness will be more, strength and stiffness will be more here. So because of the change in stiffness, the building is expected to collapse by soft story failure. Okay, so that's what we mean when we say soft story and weak story. Lack of stiffness all along the head of the building is a soft story failure. Lack of strength between the floors results in weak story failure. Okay. So number one reason is load path. Number two is open ground story. Okay. We will see next deficient. Discontinuity shear wall. Okay. So these are all shear wall. Actually, I already told shear wall is a wall prescribed for earthquake resistant. Actually, it is a solution to earthquake resistance because it has got more stiffness. To increase the stiffness, we should use the shear wall. Actually, shear wall is nothing but a concrete wall. Okay, we place it all along the height of the building. Okay. Now, in case if we have the shear wall, only up to this portion, it is not extended up to the ground floor. In this case, it is very dangerous. Even though you use the shear wall only at the top floor, but the bottom floor you are not using the shear wall. It is very dangerous. So it attacks more amount of horizontal forces. The building is suspected to fail. Okay, avoid a discontinuity in shear wall always. So there should be continuous shear wall. Okay? There should not be discontinuous in shear wall. All along the height of the shear wall should be there. The shear wall should be provided from the foundation to the top story. Okay, so that is what the concept here. So the problem is a discontinuous shear wall. The solution to the problem is avoid the discontinuity. So next is a short column twisting of the building. We'll so go to this 730. Okay. The building is getting twisted. Why it is getting twisted? Anybody? Suppose if you have symmetric building in plan, you have the center of gravity and the center of rigidity. There is a point called the center of gravity. There is a point called the center of rigidity. Center of rigidity, sorry. Okay. So the center of gravity and the center of rigidity, if it is available at a single place, if it is located at a single place in a building, the building will not damage during earthquake. Suppose if in case of symmetrical building in plan, it may be rectangular or square, we may find the CG and the CR at a single place. CG is the point where entire mass of the building is expected to concentrate. CR is the point where entire stiffness of the building is expected to concentrate. Okay. In case of unsymmetrical building, suppose in this case, we have center of gravity here, suppose. Center of rigidity is here, suppose. So you'll find the eccentricity between these two. So the eccentricity causes a rotation of the building. Suppose earthquake forces are acting in this direction at the CG. See, this force multiplied by the eccentricity will rotate the building in clockwise direction, anti-clockwise direction. So this P multiplied by E will be the twisting moment. Will rotate the building. Okay, in this case, the building will get twisted. For the twisting moment, we are not design the building actually. The twisting moments are expected to develop only during earthquake weeks. Okay, so when the CG and the CR is not at a single point, the twisting moment is expected to develop in a building. So we want to avoid the eccentricity. So that is why the CG and the CR should be at a single point. If you are able to make the CG and the CR at a single point in a building, okay, you can avoid the twisting of the building. Is it okay?
Yes, sir.
Okay,
Yes,
thank
sir.
you. So look at this. Actually, there is a swing. The child is sitting at the corner of the swing. So because the swing, in case if you look at the plan, the center of gravity of the swing is at center. Center of rigidity also at center. When the child is sitting at the center. So that time when we the swing is swinging, that time child is not expected to fall. Yes or no? When the child is sitting at the center of the swing, okay, the center of gravity of the child is center. Center of swing, center of stiffness is also center. So the eccentricity between CG and CR is 0. So that means the child is not expected to fall. But the same child, when she is sitting at this corner of the swing, the center of gravity will be at the corner. The center of rigidity will be at center. So there will be eccentricity between these two, which causes the rotation. That is why this child is expected to fall. Is it clear now?
Yes, sir. Yes, sir.
The child is falling because the CG of the child is at the corner, center of stiffness at the center. So we find the eccentricity between these two. So the eccentricity causes a rotation. Okay. So because of the rotation only this is falling now. So in case if you have the symmetrical building, okay, constructed, we say it's earthquake resistant, but during the usage time, we are storing the high equipment, highly loaded equipment or a library building at the corner. Rest of the buildings are loaded. So that time center of gravity is shifted to the corner. Even though building is in symmetric fashion, the CG and the CR will not at a single place. The building is expected to twisted. It will get damaged. Is it okay now? So it is not only the constructing the building for earthquake resistance. During the usage also, usage of the building is also matter here. Okay, CG should not get disturbed. CG of the building and the CR of the building should be at a single point. Then only the building can be safeguarded. Okay, now look at this swing now. Okay, so the length of the rope is a different length. Earlier it was having same length. So the column also will have same length of the column. You have the floor now. Okay, we have the floor now. We have the same length of the building. So just to replace this rope with the column, the swing portion of the slab. Okay. So in this case, the building is not expected to fall when the center of gravity and the center of rigidity, etc. But when the center of gravity is shifted to corner, then only the problem takes place. Okay. Now, the rope length is varying. So that means in the sloping terrain, your column height is also varying now. So in such cases, the short column is expected to get damaged. Short column. Here also again, even if the child sits at the center in the swing, she is expected to fall. Why? Because the CG and the CR will not be at center in this case. CR will not be at center because of the unsymmetrical rope. Okay, the same way in case of building also. In case of sloping terrain, unsymmetrical length of the unequal length of the column results shifting of the center of gravity. Okay, so we will not recommend this type of building during earthquake resistance. So what we can do is we can increase the stiffness of the short column. This column stiffness we can increase compared to long column. So that means size of the column should be shorter portion should be more compared to long column. In such cases, it can be avoided. Otherwise, it is not possible. Okay. So the see simple. If we take a table whose CG and CR at a single place, so in such cases, it is not expected to fall. Okay. But if we have a symmetrical shear wall, like an additional compartment, in such cases, the center of gravity is shifted. Center of rigidity will be somewhere else. So that results in rotation. The table is expected to get rotated. Same with the building also. So the torsion forces are expected to happen. Is it clear now?
Yes, sir.
Yes. And now it's already 7:30.
Yes, sir. Yes, sir. Yes, sir. Sir.
Yes. Any question? Shall
No,
we
sir.
continue or?
Sir, 10 minutes will wind up, sir. Within 10 minutes, sir.
Okay.
10 minutes.
So
Okay.
I will go some fast Okay.
Yes, sir.
So
Yes,
now
sir.
we have discussed at least 2-3 points. Number one is we should avoid the open story at the ground floor. Okay. Number two, the load path has to be complete. So whatever the external loads are available, that needs to be transferred to the soil without any dissipation. And we should not have the discontinuity in the shear wall. Okay. And the twisting of the building should be avoided. The twisting happens because the CG of the building and the CR of the building is not at a single point. Okay, if it is a different location, the eccentricity between these two causes a moment, twisting moment. This twisting moment we had not taken in our design. Okay, so we think that only downward force, live load, dead load, accordingly the bending moment shear force develops. Accordingly, we go for design. But here in this case of twisting moment developed when the waves propagate underneath the structure. Okay, so these are all the problems. Problem. So a little bit regarding the liquefaction also we can see our building configuration. So many things are there. I spoke to discuss. We will not having time, I suppose. Okay. In the village sites, we have this type of roof. Okay, village sites. In case if it take case of this portion, this building. Okay, when the earthquake waves propagates in this direction, this gable and wall is suspected to fall inside the building. Okay, but this wall will be safe. This wall will get damaged. It will be toppled. Yes or no? Okay, so this is very dangerous in this case. So in villages, we can witness this type of building now. Maybe, okay, we have the pitched roof type of thing. Only two sides are having inclination. But what we recommend is, so instead of having two sides inclination, we can have the inclination to force all along the four sides. So this we call a heaped roof. The heaped roofs are recommended in case of masonry buildings, in case in villages. All four sides we should have the inclination. Okay, we should not have the gable and wall here. Otherwise, to understand this damage, let us take a TV. You are shifting your building. Okay, we are shifting your house. So you want to shift the building, TV in your building. So you have the TV. When you are shifting the TV, so what precautions you will take? You will not keep the TV as it is in the van, isn't it? What you will do now? The TV will be put inside the box. Okay, TV will be put inside the box, and we will have a thermocol sort of things. Okay, in the side base. Then we will tie the entire box with the rope. Okay, why do you do that? We just keep the TV in a box without having a thermocol. What is going to happen? Anybody? So when we keep the TV, okay, in a box, a box with the TV, when we keep it in van, okay, what is going to happen? Why the TV is suspected to damage or not? Without tying the box. Yes or no?
Yes, sir, there will be damage, sir.
Damage.
Without
Why
thermocol.
the building is, why the TV is getting damaged? Let us suppose that the TV moves by 10 mm. Okay, but the box, if it is moving same 10 mm, the TV is not expected to get damaged. Okay, but it is not likely to happen. When the TV is moving 10 mm, the box is expected to move even 6 mm or 4 mm. There is a relative displacement between the TV and the TV box. That is 10 minus 6, 4. That relative displacement is the reason for the failure in case of masonry building. Okay, your wall will move by 10 mm, your slab will move in the opposite direction by 4 mm or 6 mm. So the relative displacement between the components in the masonry building is the reason for the failure. So that is why what we need to do is we have to tie the entire building with the band, plinth band, okay, the sill band, like floor band. Likewise, we have to use the band to tie the entire building with a band. So that means when the earthquake wave propagates under the structure, the entire building moves as a one unit. There won't be any relative displacement. So you have to tie entire building with the band. We can make use of a plinth band, sill band, floor band. We can tie the building. It all depends upon your economic cost. We have more amount, we can go for a number of bands. Okay, the tying of the building is very much important, so that the relative displacement can be avoided. There will be a monolithic movement of a building. So all the elements in the building will move in the same displacement. So by tying the building with the band and using the hipped roof, so that will help us to avoid the failure in a masonry building. Is it okay now? So these are all the gable end wall which got damaged during the earthquake in Bhuj. Okay. Okay. Shall we stop here?
Yes, sir. Yes, sir. Yes, sir. Please, sir.
So this is
Now
what the
we-
band.
Yes, sir.
So you see, if we witness this building is not damaged in the Bhuj, which was used by band, because the band used everywhere. Okay. This building was intact in Bhuj, whereas the rest of the buildings got damaged. So that is why the band is must in a mason building. Okay. So the horizontal band, rental band, okay, roof band, floor band, plinth band, the மாதிரி we have to tie the entire building with the band, and we should have the hipped roof. So in such cases, we can safeguard the masonry building. Okay. And we can make use of the reinforcement in the masonry building, vertical reinforcement all along the height of the building, at the corner of the building. So that is also suggested. Okay. I suppose it's too much. It's already 7:45. Okay. Actually, I want to discuss so many points. So we will stop here. Okay. Any question? I wanted to hear so many questions from you. Any questions? So the takeaway from the discussion is number one, we have to avoid the open story at the ground floor. The reason being is shear accumulation will be maximum at the ground floor. So we should have the more shear strength at the ground floor. Okay, so open story should be avoided, number one. Number two, if you have been given a plan, we should be able to calculate the center of gravity point and the center of rigidity point. So the location of the CG and the CR will decide the failure. The location of CG and the CR, if it is at a single place location, the building is not expected to fail. That's how the temples and the church buildings are survived, have survived during the past. CG and the CR, all historical building, if you look at the historical building, CG and the CR will be at a single point. So that is why the building was not it's not damaged. So, but after it, we designed the building with a number of open story or any space unsymmetrical building we give. So the CG and the CR will get dislocated, and the eccentricity results a rotation of the building or twisting of the building. So we should avoid that. Okay, twisting of the building. And we've seen only pitched roof in case of masonry building. Okay, we will see so many points are there. Okay, we will discuss one by one now, in case if we happen to see any chance further. Okay.
Participation.
Madam,
Kindly,
any question?
kindly ask your questions and queries in chat box.
Chat box.
Sir,
Good
they're
evening,
asking,
sir.
sir. It's a strong column and weak beam concept not suited for seismic region.
Okay. Strong column and weak beam. We should have a strong column and weak beam at the seismic region, wherever the zones are more. Zone 5, zone 4. Always we should have the strong column. Why? Because the accumulation of the shear is maximum at the ground floor. Okay, the column, in case if you have the size of the column is more, okay, it can take the lateral forces. The size of the column is less, it will have less stiffness. The size of the column is more, we have the more stiffness. And also in case of strong column and weak beam, okay, the cracks are expected to be available in all along the building, but the building will not fall. But in case if you look at the other way, weak column and strong beam, only the ground floor columns are expected to damage, but the building will be okay. The entire building is expected to collapse. in case if you have the weak column and a strong beam. Okay, entire building is supposed to collapse. That is why it is not suggested to go for big column, strong beam. Okay, it is better to go for strong column, big beam.
So
Okay.
good evening, sir. I'm having one doubt, sir.
Yes, yes.
Okay. So assuming my building is located in an earthquake-prone zone, sir,
Okay. Okay.
and the same location is expected to have cyclones also, sir.
Okay. Okay. Very good.
Yeah,
Very question.
so
Good question.
so for which disaster I should design my building to resist, sir?
Very good. Very
Should
good.
I consider only earthquake or cyclone?
Okay. Okay. We will see that. Okay. So in case of earthquake, we witnessed this just now. In case of earthquake, the inertia force is the reason for the failure of the building. That means the horizontal forces which are expected to act at each and every floor. Okay. So that is where the shear accumulation is happening now at the bottom. So that means the ground floor should be strong enough to withstand the shear, which is expected to develop. But in case of cyclone prone area, so you have the building. Okay. So the air pressure is expected to act from the bottom. The building is expected to get lifted up. So that means we should anchor the building in case of cyclone prone area. Is it clear now? So normally what we design is normally the live load and dead load should be transferred to the soil without any dissipation. From the slab to beam, beam to column, column to the foundation, foundation to the soil without any dissipation. Okay. But here that is not sufficient. In case of earthquake, we are expected to happen, expected to get developed by inertia forces. In case of cyclone, it is upward force, air pressure, which are expected to get lifted up. The buildings are expected to get lifted up. We need to anchor the building. So in my suggestion is similar to look at the map actually, seismic zone map and a cyclone zone map. So we have to take both the cases. We cannot have structure constructed for earthquake resistance and cyclone resistance. Is it clear now? We cannot have single structure constructed for both. It is not possible. So you should go for either earthquake resistant or cyclone resistance. So
Okay,
that you will have to decide.
okay, sir. Okay, sir. Thank you, sir.
You will have to decide because we cannot have single structure constructed for any type of disaster like earthquake, tsunami, cyclone, landslide. So the design demands actually different. So in case of a cyclone, the upward force, upward pressure which gets lifted up the building, that is why the building itself getting damaged. So means we will have to anchor the building in case of cyclone. But in case of earthquake, it's not like that. The horizontal force which are expected to act during earthquake. But in case of tsunami, the water waves are expected to pass through the building. We require to have the open soil at the ground floor. So we cannot have a single structure constructed for earthquake and tsunami or cyclone. Okay. So it depends upon the wind map, wind zone map and or a cyclone zone map and earthquake zone map. We have to decide. And the occurrence of earthquake in the past history. What is the frequency of occurrence of earthquake? So that we have to look at accordingly. We should decide. Okay. But every time the cyclones are expected to happen. Okay, 3 months in a year. So the cyclones, so we can expect a cyclone frequently. So it is better to go for cyclone resistant building all along the seashore. Okay, instead of going for earthquake resistant down south the India. Otherwise, in case if the building is seismic zone 4 in North India, it is better to go for earthquake resistant. Okay, is it okay?
So shall we conclude the session, sir?
Okay.
Okay, sir. Karthik,
Okay.
sir. Karthik, sir.
Yes, ma'am. Yes, ma'am, I'm in here. As we conclude in this enlightening session on risk management for earthquake disasters, as a part of AICT sponsored a ATAL faculty development program on resilient infrastructure for cyclone-prone areas, it's my privilege to extend my heartfelt vote of thanks. First of all, I would like to express my sincere gratitude to our esteemed guest, Dr. R. Ponnuturai sir. Sir, your invaluable insights on earthquake risk mitigation have provided a deeper understanding and how to enhance the infrastructure resilience in disaster-prone areas. Your vast knowledge and research expertise in enriching the session, sir. Thank you, sir.
Thank you.
Thank you so much.
Thank you.
Thank you so much for last minute acceptance, our convenient. Thank you so much, and you are getting so much depth knowledge in earthquake resistance. Thank you so much, sir. Once again, sir.
Okay, thank you, ma'am. Thank you. Thank you, Ananda. Thank you, Ananda, for patient hearing for 2 hours almost. It's not possible to sit at a single place. Thank you, Ananda. Thank you. Thank you.
Thank you.
It's a
Thank you.
pleasure, sir.
Thank you.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir.
Once again, thank you all for your presence and participations. Looking forward the next session also. Thank you.
மேம் கண்டினியூ பண்ணிடலாம் மேம். அந்த வெல்கம் மட்டும் பண்ணிடலாம் மேம், ப்ளீஸ் மேம். கார்த்திக் சார்.
Yes, ma'am.
Next, our resource person is in lobby only, sir.
Online, ma'am.
So
Okay, ma'am.
continue the session, sir, please.
Okay, ma'am. Thank you. Thank you. Thank you for the opportunity. Welcome to the 6th session. Ladies and gentlemen, it's our great honor to introduce our esteemed chief guest for this session, Resilient Infrastructure for Cyclone-Prone Areas. We are privileged to have with us Dr. Tenmali, Professor and Head of the Department of Government College of Technology, Coimbatore. Dr. Tenmali ma'am is a highly respected academician and researcher in the field of structural engineering with expertise in disaster-resistant construction, sustainable building materials, and infrastructure resilience. Her contribution in civil engineering education and research have played a crucial role in advanced innovative solution for disaster mitigation. Today, she will be sharing her insights on construction futures of cyclone-resistant buildings, a topic of immense significance in ensuring structural safety and mitigation damages in cyclone-prone regions. Her expertise will provide us a deeper understanding of the best practice and design principles essential for resilient infrastructure. Let us all extend a warm welcome to Dr. Tenmuli ma'am. We welcome you, ma'am. Ma'am, kindly unmute your mic, ma'am.
Ma'am?
Yeah. So
Yes,
can you
ma'am.
hear me?
Yes, ma'am.
Thank you very much. Thanks for
Thank
your
you.
very warm welcome.
Thank you, ma'am.
Thank
Thank you, ma'am.
Yeah, very good evening to one and all present here. And first of all, my appreciations to the organizers of the program for having chosen a very nice topic. Normally, people are choosing the earthquake resistant design of structures, disaster management, and the maintenance and rehabilitation of structures. In all those things related with only to the seismic area only, right? But whereas in Tamil Nadu, we are less prone to the almost nil. Am I right, madam? So we are just having
Yes,
only, we
ma'am.
are exposed to mostly the flood and cyclone, right?
Yes, ma'am.
Almost
Yes,
in
ma'am.
every year or so, right?
Yes,
Because
ma'am.
as
Yes,
far
ma'am.
as the coastal regions are concerned, more towards the Chennai, Kadalur, Nagapattinam, all those areas are highly affected by this kind of serious cyclones and flood, and every year we are affecting due to that. Of course, we are in the last year also we felt a very huge cyclone in the last year, because after 2015 it was we felt the losses in the property and in other ways also. So in that sense, you have chosen a very nice topic, which will be very useful to the faculty and also to the higher education department also. So my congratulations and appreciations for having chosen this topic, madam.
Thank you,
now,
ma'am. Thank you, ma'am.
And also my sincere thanks to for the opportunity given to me. Thank you, madam. I just share my screen now.
Ma'am. Yes, ma'am.
Madam, are you able to see my screen?
Yes, ma'am.
Yeah. So,
Able to see our slide
okay.
one. Okay.
My voice is audible? Am I
Yes,
right?
ma'am. Yes, ma'am. It's audible
Yeah.
only.
Yeah. So my topic of discussion now will be the construction features of cyclone resistant buildings. So I organized my presentation this way. So I am going to tell little about the disasters and also what are the different types of cyclones in the various periods we have, and also then to the design principles, basics of design principles as per the cyclone resistant buildings are concerned, in addition to the some of the construction features. So this is my agenda here today. So as far as you all people know very well about the different kinds of disasters, because the previous speaker also well delivered about the main type of disaster, earthquake. So to start with that one, so we know all about this earthquake and cyclone, flood, fire, and landslides, liquefaction, and tsunami. Of course, if we happen to hear about fire, so recently we hear about the Los Angeles fire, right? So like that, we are having so many natural disasters also we had nowadays. Right? So as far as Indian climate is concerned, we normally face earthquake, tsunami, and this kind of flood and cyclone. Right? So in which our area today is to discuss about the cyclone resistant building construction. So as far as we all know that this proper design mitigates the environmental degradation and it preserves the essential infrastructure, because we all know that the cyclones are the most destructive natural phenomena. It extends over a wide area, and then, due to this cyclone, it not just due to only the winds we are affecting, but it creates some a certain kind of secondary effects. So secondary events such as the very storm surges, flooding, huge floodings, landslides. So due to that landslides and soil erosion and tornadoes, so due to that only our structures are getting affected. So these are some of the damages caused by the recent cyclone Varda. I hope many of you heard about it. And this is again another view of the very same cyclone. And we could see how the electric poles and all the houses have been affected due to this cyclone. And this slide shows the features about the cyclone Fani, which has happened in the year 2019 in the Odisha and Andhra Pradesh coastal region. So as far as the structural impact is concerned, it has damaged more kinds of roads, bridges, public buildings, and also the main building, community buildings like community towers, communication towers, electric poles, and water supply networks, sewage systems, railway lines, like that. So many common buildings have been affected. All those poorly constructed houses and coastal embankments, all those things have been collapsed also. So our response towards this is we have to reconstruct, and also this because all those lines will be collapsed. So the reinforcement of the bridges and highways to withstand the future cyclone impact, that also we have to provide. So we must do the repair and the rehabilitation activities also. Right? And the deployment of mobile power grids and the underground cabling to prevent the power outages during the storms. So during that time, we also heard about in the last year also we heard from the Chennai people that so nobody could be able to get connected, right? So how the people might have suffered, that we have seen using the many media. And similarly, as far as the next event, Cyclone Amphan in 2020 is concerned, which was happened in the coastal region, West Bengal and Odisha. So severely affected buildings and other infrastructure we have seen. And also we have to strengthen them. So before doing that one, so instead of coming for the after effects, so if it is constructed very well in the earlier period itself during construction, if it is taken care of, then we could save the lives, properties, and the other things also. So this is about the another cyclone in 2021 along the coastal region Gujarat and Maharashtra, and in Varta 2016 Tamil Nadu and Andhra Pradesh region, and had in 2014 via Andhra Pradesh and Odisha. Yes. So coming over to this introduction, so you all know about what is cyclone now. So cyclone is nothing but it is a weather condition in which the wind rotates around the center point, so that a low pressure will be developed, and also the wind motion will be in the counterclockwise or in the clockwise direction. It is based on either the northern hemisphere or it is a southern hemisphere. And normally the buildings can be categorized into two types. One may be the catastrophic failures, and another one may be due to the component failures. Right? And we all know that the cyclone prone areas are along the coastal region only. So mainly in the Tamil Nadu, Kerala, Andhra Pradesh, West Bengal, Odisha, these are the areas which are highly affected by this cyclone, vulnerable zones. So as far as the importance of designing the buildings to withstand cyclone is concerned, so this is all the buildings should be designed to withstand the strong winds, right? And I hope many people happen to hear that. See, in Chennai, in the last year beginning, I think, in Thenampet region, one of the building glass facade completely fall down due to a heavy wind. So it was not due to the rainfall and other things, but in certain day, in any one day, I think heavy, strong wind was occurred. So due to that, the complete facade, glass facade, have fallen down. I think it is a G+6 storied building. So like that, so each and everything we have to taken care of. So this is next one is about the heavy rainfall and the associated flooding with cyclonic storms. So these buildings incorporate the aerodynamic shapes, reinforced materials, and elevated foundations to minimize the damage and ensure safety. So what we have to do is the cyclone-resistant buildings should be designed to help us to reduce the loss of life and property. That should be our main aim. So they have to provide safety to our occupants of the building, and also so that if we are taken care of that, so we could save the economy. That is, we could save our property also, and ensure a quicker and safer environment to the public. So as far as the design is concerned, so the first and foremost thing come to our mind is nothing but the design loads. So what are the types of loads that we have to consider? That should be our question, right? Because you will be given an area, and in that the type of building also you know. So further, what type of building and what are the considerations we have to take care? So that we should know. So for which the main basic design loads are nothing but the dead load, imposed load, wind load, and earthquake load. So in addition to that, our recent code suggests many other types of loads also, almost 11 categories of loads. This IS 456 2025, which is in the draft version now, that talks about the other kinds of loads also. But anyway, as far as the cyclone resistant buildings are concerned, we have to bother about both the wind and earthquake, because these both the things causes the lateral effect, and for the worst combination we have to design the building. So these are the different types of loads system may be subjected to. Right? So the first one is about the dead load, which is to be referred as per IS 875 part 1, and imposed load as per part 2, snow load including the avalanches and those places part 4, earth pressure load from part 5, and the construction load should be referred from part 2, and pre-stressing load, because this is having a separate code 1343, but now as far as this new code is concerned, it is merged with IS 456 itself. So just after the release of this draft version, then it will be withdrawn. The earlier version, the IS 1343 pre-stressing code, design of pre-stress concrete structures, will be withdrawn. So that's why it is put here as class 8.2.1.3, which refers IS 456 2025 of draft version. And similarly, wind load to be considered from IS 875 part 3, and liquid pressure loads IS 875 part 5, and similarly machine vibration load, blast load, impact load. So these are the different kinds of loads a system is to be referred, is to be maybe subjected to. So based on the type of structure, we have to consider the loads, and accordingly for the different load combinations, for the worst combination, we have to finalize the design system. So the load combination for this kind of structure may be either in our region, it may be either dead load and live load. In addition to this dead load and live load, it may be due to wind load or maybe due to earthquake load. So yes, certain up to certain height, the wind load may be predominant, and for certain regions and for certain height of the building, the earthquake load may be predominant. So that maybe we can calculate based on the design considerations only. So as far as this earthquake forces are concerned, you may know that F equal to ma, and also the wind force is to be calculated based on the intensity of wind multiplied by the area of obstruction. So as far as the design principles are concerned, so we have to differentiate between this cyclone resistant design and also this earthquake resistant design, right? So I'm not going much deeper into this one, right? So by hearing the class, that too is a rough, a heavy subject by 8 p.m. will be a little bit difficult. So I am taking in the lighter sense only. As far as this cyclone resistant design is concerned, you have to provide no damage condition. But if for the earthquake resistant design is concerned, you can permit the damage, but there should not be any collapse, right? So this is the main difference between the cyclone resistant design and earthquake resistant design. And when we compare this earthquake versus cyclone, so during the earthquake, the lighter building and the roof, the better will be the performance. But the reverse is the case as far as this wind resistant, cyclone resistant buildings are concerned, right? So the lighter roof here during the earthquake regions would not induce as much load on the walls, and the walls would be able to transfer the load also easily during an earthquake. But this cyclone kind of thing, as the heavier the roof, the better will be the performance. So otherwise what may happen? Because it may lift now, so the uplift will be acting there. So the thatched roofs or steel frames, or if it is made of some steel framed building, maybe having a lightly corrugated sheetings, industries kind of thing. No? So those things may be uplifted. So that may be a reason for the entire collapse. So this is the wind and cyclone and earthquake hazard map. The zones are shown here. And these are this Indian map, which just shows about the cyclone area, shaded in the different colors. Yes. So as far as the wind loads are concerned, I hope this equation you all know. As per our IS 875 part 3, we used it to calculate this design wind. We will take up this value of the basic wind speed for the with reference to our area. So this wind speed Vz will be calculated based on VB, basic wind speed, multiplied by the probability factor, terrain factor, and topographic factor. So based on this, the design wind pressure Pz will be calculated as 0.6 into Vz square. And as far as the wind speed and damage relationship are concerned, so if there are 5 different categories are defined here from 1 to 5. So if the speed is of 33 to 42 meters per second, then miles per second, then it will be, the damage will be considered as minimal. And that is, the second one is nothing but miles per hour. So if the 74 to 95 miles per hour is the wind speed, then the damage is considered as the minimal one. So as far as the second category, that is the moderate is concerned, it may range from 96 to 110 miles per hour. And similarly, if it may be in the range of 111 to 130 for an extensive damage. So beyond that 131 up to 155 miles per hour, it may lead to an extreme case. And beyond that, after 155 miles per hour, then it may lead to a catastrophic failure condition. So these are the different wind speed versus damage relation is given as per the code. So this is about the hurricane wind scale. So this is categorized into 1, 2, 3, 4, and 5. Based on the different miles per hour, it is defined. So what kind of failure will come, that is shown here. So here minimal one, a lightly disturbed thing, non-structural damages. And here in addition to non-structural damages, some of the cracks and other things may happen. And here some kind of structural damage may also occur. And this is lead to a complete collapse. So now what is the difference between a cyclone, hurricane, and a typhoon? Because all are depending on only the wind speed alone. No? So what will be the major thing? Right? So because all these things are essentially the same phenomena called the weather. Right? But where it occurs, that is the only thing. Based on that only it is named. So if it is a hurricane, then it may occur in the Northeast Pacific Ocean and the Atlantic Ocean here. And if it is called typhoon, then it will be in Northwest Pacific Ocean. And for cyclone, which we normally get in the South Pacific Ocean and the Indian Ocean here. So this is how the various things, hurricane, typhoon, and the cyclones are defined here. Yes. Coming over to the performance of building. So here I am just dividing this into two categories. One is for the non-engineered buildings, and whereas those things are all highly vulnerable. And the other one is coming under the engineered building, whereas it is a well-designed one, and it gives a the performance of those buildings are highly satisfactory. And another thing is nothing but the poorly designed one. It is a vulnerable one. So now what we are going to do for a non-engineered building and an engineered building, that we are going to see. So as far as the non-engineered buildings are concerned, it won't have any defined rules for construction, right? So this is the finest example for that. So this is damage due to a cyclone. This in the rear wall, completely it is collapsed. So due to this collapse, the entire part of the building has gone down, right? So because of this outward wind pressure. And this is again another example. So mainly this clay tiled roof, no? So that is blown away. So that's why the entire thing fell down. And this is due to the erosion here. So erosion due to the excessive rainfall. So if the continuous rainfall occurs, then what may happen? Naturally, if it is a low-lying area and here you are having the house, right? So all this soil may be eroded, right? So what the continuous erosion may cause a failure of this structure, right? So that's why this is supported by a kind of sandbags like this. And this is again another erosion is shown here due to the excessive rainfall. So if it is left as such, then if it is a framed building, then the things may be safer to some extent. But if it is a masonry building or other load-bearing structure, and if it is not supported well, then it may lead to a failure. So coming over to this structural configuration, we assume that it is a very important factor for better performance. So certain recommendations are now given to accelerate the materials and also to the better performance. So as far as this non-engineered buildings are concerned, so we have to provide the planning as a symmetrical one. Normally, as for how we are concerning for this earthquake resistant building, in the same way we have to we must first fix the shape of the building, and always it is preferable to choose a symmetric building. Or otherwise, if you are not able to choose the symmetrical building, so we have to consider those balanced distribution part, everything in a pakka manner. And the second point is we have to restrict the height of the buildings to either 1 or 2-storied building. So not necessary to restrict the height, but if you are going beyond that, proper care should be taken care of based on by providing certain bandwidth, everything. And another one is ensure that the lightweight floors and roofs are securely fashioned to the walls. Yeah, this is a very important part. So if you are providing the mason non-engineered building, and that too is a load bearing type, right? And also if it is of either ground floor only or the first floor only, you have ground floor plus first floor you have to ensure that the roof is well connected with the wall and wall is well connected with the other kind of things, let's say floor, and also the openings wherever you are having, and also to the doors and window openings, and then it is finally to the foundation, right? So those things are all should be well connected. And the lightweight roofs should have a hipped shape sloping in 4 directions rather than a gable shape, right? So this lightweight roofs should be not less than steep than 20 degrees to improve the wind resistance. And similarly, the last point will be the lightweight roofs should have a minimum overhang. Normally, the cantilevering type is to be avoided because it may be susceptible to failure. Okay. So in fact, if it is, it would be better to have a no overhangs and to introduce a parapet. The need to shade windows and doors from sun and rain may be made by the separate canopies. Yeah. Coming over to this performance of engineered buildings. So these are the different cases. So timber houses, steel framed buildings, masonry houses, and reinforced concrete frames. So the first one is about the timber houses. So you are able to see a catastrophic failure of a timber house, right? So the inherent vulnerability of this lightweight timber houses, coupled with poor connections mainly, right? The rafters and the roof member, and rafter with the purlins, and also the purlin with the grits, and this purlin with the walls, and the wall with the foundation may not be in a good connection. Mainly all the steel framed connection buildings and also this timber houses should have a good connection. These connection failure may lead to a complete disaster. So as far as this, the very same thing, what I told you for the timber houses, hold good here again, right? Of course, this may be having a good resistance, that is the integrity may be here good. But whereas, see, in the previous case, even the rafters also along the bolt line, it may be having a horizontal split of failure. So those kinds of things should be avoided based on the high quality material and also the high quality nut and bolt, and for proper spacing of the bolts. So as far as this steel portal framed buildings are concerned, see, always we have a misconception that the loss of cladding relieves the loads from building frameworks. It is not so. Definitely it is not so. There are several circumstances where the opposite is also the reason, where the wind loads on the structural frame increases substantially with the loss of cladding. So usually the weakness in steel frames is mainly the connection point only, right? So we have to safeguard against the all sort of connections here, right? So this beam to column to again at the top rafters, and also the purlins, right? Wall cladding units, and also to the some way in some of the industrial buildings you may be having the gantry girders also. So that should be well connected with this column and beam, and also it should be tied well with the foundation here, right? So if the load is properly transferred to the foundation, then it may be it will behave in a good manner. So as far as the masonry houses are concerned, these are usually regarded as being safe in cyclones, but there are so many examples where the loss of roofs has triggered to the entire loss itself. So if the roof is not heavily constructed, then it may lead to the part failure or the entire building failure itself. And these are the things that we can take care of, right? So now what it is suggested by the previous speaker also, no? So we have to give this kind of reinforced brick masonry here, right? So all these lateral loads could be taken care of if it is reinforced well, because it may be subjected to both tension and also compression, right? So in such cases, to guard against this lateral forces in a severe manner, then you have to arrange this bricks in this fashion, leaving a hollow space here. So here at this point, you can space here a steel rod either 12 mm rod or 10 mm rod based on the requirement. And this spacing could be filled with a micro concrete. This is the entire picture of the masonry house. So here you are able to see both in the horizontal side and also in the vertical fashion, you are able to see many steel rods, right? So in this, either it may be a brick or it could be a hollow blocks or any kind of block. So in that you have to find a location, or you must you must construct in such a fashion that you are able to provide the vertical steel rods, and also you are able to, of course, providing the horizontal steel rods and ties may be easy, right? But you must provide the vertical bands also here. So in the same way, the links also properly to be provided. So here in every band, at least every 3 blocks, we have in rows, 3 rows of blocks, we have to provide a horizontal band like this to take care of this heavy area where it is prone to cyclones. And also this kind of foundation, T-junction joints should be provided well. So this joint should be taken care of. This kind of thing should be provided. Yeah, this is shown in a closed manner. So these are all the hollow blocks. In this hollow blocks, of course, you are having a hollow space here. So in this space, we can connect a steel rod. We can provide a steel rod, and this space should be filled with a cement micro concrete with baby jelly only. Yes, as far as this wall openings are concerned, so this topic is also very important one, because the openings provide as of the light and ventilation, but it is a very weak point as far as the earthquake, both earthquake and the cyclone prone areas are concerned, right? So whenever you are having an opening, then you have to provide the top and bottom reinforcement, and also this should be connected with the side wall well. So here the whole first arrangement should be properly locked here, right? So you can have the openings in the load bearing walls at least h/6 away from the h/6 height away from the inner corners, and avoid openings just below the roof level except for 2 small vent you could give. Right. And the weak doors or windows on windward side can increase the roof uplift forces also. So from which we have to take care of. And you can use the strong holdfast, proper locking, and ensure the adequate anchorage also. Yes. So coming over to this engineered buildings, either the components may fail or the entire system may fail, right? So the components, as far as the entire the component failures are concerned, right? Roof sheeting or roof tiles or rafters, connections, walls, foundations, and windows and doors. So these may be the various components you may get the failures. So as far as the roof sheeting is concerned, this is one of the main commonest area where I have shown some of the pictures also. And this is also another picture wherein the corrugated metal sheet roof is simply blown. Right? The causes teared off in some places. And the causes may be due to the inadequate fashioning devices. Mainly the joint or the connection may be inadequate here. And in addition to that, you may be having a thickness of the sheet may be lesser here. Right? So this is about the roof sheeting. And as similarly, if it is a roof tiles also, the connection should be highly good. And uplifting of roof or house. So roofs that are not anchored properly can get this upliftment like this one during a cyclone. And this lightweight temporary shelters which are not held properly also may blow away. And similarly, what in the previous slide I have shown, see galvanized iron sheeted. It is sheeted roofs or tiled roofs could blow away if the anchorage is not properly done. So the pressure of the wind, say here, this is a tiled roof, right? So here you are having a window opening, door opening. So from this adjacent side of the either the window opening or door opening, you may be expecting a heavy wind, right? So this storm may just give an upward pressure here. So that may uplift the clay tiles here, right? So this may be the cause for this kind of failures. And coming over to the walls must be securely tied here to the foundation to prevent the wind forces lifting up the entire building, right? Or it may be blown away. So here the connections are given properly, right? So this kind of connection is good, whereas this is not at all provided well here, right? Toenail connection. And similarly here we have to provide the L-shaped steel patta should be given here. See, like this. And the length of encouragement also as per the Indian standard provisions. So here it is provided, no? So this kind of connection should be provided in the cyclone prone regions and also in the hurricane prone regions based on the vulnerability. And as far as the foundations are concerned, see, the uplift forces from cyclone winds can sometimes pull the buildings completely. See here, this is very small foundation. It is very small, too small for this structure. Right? So it is completely fallen down. So these kind of things should be avoided here. And in some cases the box action give very high integrity. So in the last picture we have seen about the very small build foundation, right? So which is simply placed over this one. This is I section, right? So for a cycle shed or in this petrol bunks, we could be able to see a kind of structures or in railway stations, right? But the pedestal provided here is highly insufficient, right? So that should be anchored well with the ground, and also it should be of firm. So the thickness, the material, this should be in a heavy manner. So this kind of raft arrangement may taken care of in this kind of things. So this will provide you a very high integrity. So this is the reinforcement in the concrete block wall tied to that of the foundation. So here, instead of just giving a gap here, we have to make this fully in a pakka manner. And here we are providing the concrete wall, block wall. So, and also, as I have mentioned in the earlier cases, see, you have to provide necessarily a steel rod that should go deep into this foundation, and also it should be well connected. So the foundation of a cyclone resistant building, as suggested, we can say that the foundation should be strong enough and designed to transfer the building's weight to the ground. Because from the roof, it is transferring to the beam, then to the column, and also to the foundation well. Right? It should be in a proper load path transfer. So the foundation should also be able to withstand the flooding and surge that can occur during a cyclone. So what we have to do is mainly, as far as the foundation design is concerned, we all know that it bothers about the soil type and the type of soil, how much bearing capacity it has. Right. So we have to conduct a safe bearing standard penetration test or a bore log test. Based on that, we must evaluate the depth of foundation for that particular region, and also how much is bearing capacity we have to provide. So for that only the system should be designed. So based on that, either you can take up a shallow foundation or a deep foundation based on the type of soil you are having. So if it is a liquefiable soil or a clayey soil or expansive type, then it may require a deeper foundation. So if it is a sandy or alluvial soil, you can go for a shallow type foundation. And in certain conditions, it may require a raft or strip footing like that also. Suppose in cases you have a made up soil, then in that case, either any kind of ground improvement could be done. And in addition to that, you can go for a raft. So, and as far as the location is concerned, the building should be constructed on a flat, firm, and well-drained site also. So, if it is a water point is there, then for that the accountability towards bearing capacity and depth should be given well. And in the coastal areas, the building should be constructed on the higher ground to avoid flooding. So as far as the depth is concerned, what I have told you, so it should be taken into account the covering effect of tidal surges. And the type of foundation is concerned, based on the type of soil and SBZ, we can choose the type of foundations. So as far as the other considerations are concerned, the building should be made from the high strength materials. So whatever be the type of material, nowadays we are having the ductile resistant materials also. As far as the steel rods are concerned, 500D, 550D, like the 600D ductile, 650D, all those things are available. So we can choose the relevant material, and also the high strength concrete also we have today. And as far as the new code 2025 gives us the another range only now, right? We are moving forward, but it is still in the draft version only. It is having, it is yet to come. And as far as the openings are concerned, either for the windows, you can use the impact resistant glass, because the glass is highly vulnerable material. So wherein we have to put some effort to take care of that. And the second point is concerned, the building should have a sturdy structural design with RC frames and the Pakka bracing systems. Of course, the previous speaker told you much about this soft story collapse and the bracing systems. No, so you know about the X bracing, K bracing, Y bracing systems, and all the shear wall system. So many things are nowadays available, and full steel plate also nowadays provided as a shear wall. So for the shear wall, it is based on the ferrocement material also, with the steel rods and the GFRP wrappings. So many kinds of shear wall are available, but we have to take care of that in the design. And the buildings should have a simple, compact, and symmetrical shape. It should have a steeply pitched hipped roof with little to no overhangs. And it should have a reinforced and minimized openings, and it should have a wind locks and braces also in the doors. Yeah. So these are the different types of foundations I have shown here. So this is, of course, a stepped foundation. In cases, suppose if the sloping ground, like our Ooty or Kodaikanal or something, a sloping ground is there, then we can choose this kind of stepped foundation. And this is for a strip foundation where it could support a continuous wall. And this is pad isolated foundations where you are having a firm ground, level firm ground. And this is for the deep foundation. Suppose if it is a pile or pier pile type of foundations are available under the category of deep foundation. Suppose if you are encountering with the expansive clay or alluvial soils, so in that cases, you can choose this pile foundation. So it is essential to construct a suitable foundation for a house as a stability of the building, which depends primarily on its foundation. So the foundation should be go deeper also. The entire foundation of a house should be constructed on the same soil and not on the made up soil. So here you can see the picture. See, in the first picture, part of the house is in the made up ground. That's right. So here it is marked as into a cross. So this is not at all a desirable one. And here you can just shift the building itself to the firm ground, and you are able to avoid this made up ground. Of course, you have to get a clearance of 1 meter or so here, right? In some cases, you may not be in a condition to avoid this one, right? See, you might have purchased the ground in the slopey terrain. So in that case, what you have to do is you must take proper care in this anchorage for the building with the level here. So as far as the windows and doors are concerned, the most attention is needed on the windows and doors here. But never we normally used to neglect this part, because this is not a structural element, right? Because suppose if it is a slab design or beam, or if it is a frame, or if it is a column and foundation, etc., etc. So all structural elements we used to bother. But we are not bothering about, we never bother about the type of windows and doors that we are providing. Right? So at least we have to bother about these kinds of elements, non-structural elements in the cyclone prone areas. So for which the glass windows have to be, the material should be chosen in a Pakka manner. So there are two solutions here mentioned. One is the use of impact resistant glass, and another one is cover the glass with the storm shutters. So that is also possible today, right? So you have to give attention to make it secured in its own place. So here the entire arrangement is given the lateral fixtures here. So the anchorage of the doors and window frames with the pakka holders should be provided with the wall. Right? Wall means not only the masonry part. Here I am mentioning about the concrete. Right? So these whole spots should be anchored well with the concrete, which is of higher grade. Right. And another thing is large and thin unprotected glass areas in the windows are here provided, and here you can tape it with like this. And as far as the positioning of windows is concerned, see, the windward face of the building collapses under the pressure of wind force, right? So what you have to do is you can provide it like this, right? So use of cyclone shutters and the reinforced RC frames, and you can use the impact resistant glass for windows, reduce the number of larger openings, right? So you can make it small, and sealing techniques to prevent the wind infiltration also could be done. So the next, yeah, I think it is repeated. So coming over to the design principles. So the cyclone resistant buildings are essential in the particular region because we cannot avoid, right? Because nearer to the coastal regions, all the districts and all the houses in those places are subjected to the lateral forces, right? So to avoid the men and material loss and the property losses, we have to design according to the cyclone principles, resistant design principles. So for which we have to take care of this mainly four essential characteristics. The first one is about the site selection, and the second one is about the building geometry, and the third one is about the structural integrity, and fourth one is about the roof design. So these are the planning considerations. So here, as far as the site selection is concerned, see, it is better what I have told you in the previous slide also, no? So the same thing. So you have to select a plot like this in the pakka ground, right? Firm planar region. If it is possible to choose, then you can choose that one, right? So not in the artificially raised platforms. So some ways, suppose in some cases, you may be in a position to partly fill up area. So in that areas, you have to give the ground improvement technique, then you must make it. So these kinds of things are not at all suggested for the coastal regions, because definitely so during the coastal cyclone periods, the surge may raise in even to the height of 10 kilometers also, right? So in that regions, then we have to avoid, right? So in that cases, the entire house may be affected. So planning for better buildings. So as far as the location is concerned, it is very, very important. We have to give a little choice in that matter, because due to some financial constraints, we may be in a condition to avoid that, right? So for the particular land, whatever be the thing you are having, you may be in a condition to construct that. But it is okay in that region. You have to provide all the necessary designs, steps to be taken care of to safeguard your building. So it is as well, therefore, to recognize when a building is being located in a more vulnerable area. So the rational response should be given here. And such vulnerable areas include the open-ended valleys, which acts as a funnel. So the wind tunnel effect may be there in the hilly areas. So that wind tunnel may create a more vulnerability to the existing buildings as well as the upcoming things also. So when choosing a site for your home, right? So building near the ridges to be avoided here. So whereas here it will be, so the kind of thing. So instead of this place, you can choose the home in this place, right? But in certain situations nowadays, we don't have place, right? So in that situation, you have to give proper anchorage with the ground, firm ground. That is very important, right? And also if it is also made up ground, or if it is not firmly secured, then you have to give a ground improvement technique. Nowadays, lot of ground improvement techniques are available. So using that, you can make it, and then you can make the ground stiff, and then you can proceed with the further construction. And this is about, if the same thing, if your plot is on the sloper terrain, then don't place the house like this unless it is properly anchored. Here the anchorage using the RCC column is given, and that RCC column with this terrain should be properly anchored. The foundation is very, very important. And the wind and water can dislodge the house here. And the house is best built on a flat firm site, provided it is a well-drained one. This is about the cut and fill method. In some of the areas, we may be having in a condition to mark this. We have to cut the soil and we can fill up, and over the filled up ground, we may be in a condition to construct our house. But that soil, that design should be taken care of in a pakka manner. Unless otherwise, you are able to give a good anchorage. Yes. So the second one is considered, it is a building geometry, and the shape of the building as far as the planning considerations are concerned, this is very, very important. So of course, in all the ways, we know that the square shape is pakka, right? So it is the most important, most compact one, and also it won't produce any problem here, right? And the next best one is nothing but our rectangle, and sometimes we may be having a long rectangles also, right? And also we may be having a T shape, L shape, something like that. But here also we may be having a wind tunnel effect. So that will affect this building, the corner of the buildings, so that the torsion will be created. So to avoid all these things, we have to give proper design considerations. So the best shape here is nothing but the square. And sometimes you may be having a group of buildings, row planning, and the government, the slum clearance board and the Tamil Nadu housing board are constructing the continuous row houses, no? And also some of the apartments are constructed, some villas are constructed, single ground floor only, or a two-storied building villas, like that. A row of villas are constructed in many places. So in that cases also, if it is provided like this, then the wind tunnel effect may be created. So that may be the cause to induce more forces. So this is not at all a desirable one. But instead of constructing this row houses, we can go for a zigzag planning. So this will avoid the wind effect. Right? And as far as the integrity is concerned, so you have to give importance to the material mainly, and also the designs, right? So try to use only the durable materials like the heavy RCC for both the walls and the roofs. Nowadays, here the prefabricated constructions are available. With the good connections, we can go for it. And the lightweight roofs should be avoided. And as far as the wall design is concerned, the walls must resist mainly the lateral loads due to wind. And as far as the roof design is concerned, roof type the hip roofs are recommended over the gable or the flat roofs. As they reduce uplift forces, roof pitches should be at least 22 degrees to minimize the risk of being lifted by strong winds. And necessarily we have to avoid this overhangs also. And cyclone resistant roofing, so general precautions are given here. Higher wind suction zones, corners to be avoided, and sheeted roofs. Whenever you are having a sheeted roof, the J-bolt, the connections, what I'm telling in the front, in the beginning, no? So the connections are very, very important as per the codal provisions, and as per the material also should be governed well. And this is about the very same thing, how you are giving the concrete strips here, right, to safeguard your roof. So how the connections are to be given as a J-bolt, U-bolt, and this padding, this MS flat corner, no? So how you are giving the ridge connections, this end part. So these things are explained here. And as far as the roof types and anchoring are concerned, clay tile roofs, RC strap beams, and for the thatch roofs. So this should also be given a good connection. Keep rope spacing of less than or equal to 450 mm. So all these things are codal provisions that I have mentioned. And this is about the same thing about how you are going to connect this bolt to here, and how we are going to ensuring a pakka system during the lateral forces. And here, see these things anchor each tile or each other tile to the purlin with the hooks, right? Simply we cannot place, but instead we have to provide pakka arrangement using the concrete material itself, or using the steel U hooks or J hooks. And this is all about the connections in both this purlin to rafter connection are shown here. And similarly here also it is tied well, and how we are making that this is staff arrangements are mentioned here. This is not enough to provide only in one region, but instead we have to provide in both the directions. And this slide shows you about the damaging effects of cyclone on the houses. So due to high wind pressure and improper connection of the house to the footings, it is just simply blown away, right? So footing is in the separate part and the house is toppled. Right? And similarly, here the lightweight veranda roofs, right, are more susceptible to damage due to the high wind. And here again the anchorage is not proper, so it is blown. And here when the cyclones are accompanied with heavy rain for a longer duration, the buildings may be damaged due to flooding also. So the building contents are spoiled due to the rain when roofing sheets are fly away. Coming over to the design principles, to sum up, the key principles of cyclone resistant construction are given like this. So as I have mentioned, the foundations should be deeper and it should be well connected. And RCC framed structures are to be preferred over load bearing structures. And the sloping roofs, to the extent possible, it should be avoided. And cantilever projections need to be avoided. And roof and parapet wall should be properly anchored, and the height should be restricted, and suitable wind load should be considered as per the codal provisions. And the openings also, to the extent possible, it should be less, or it should be governed well in the design and the construction. And the structure should not rest on the loose soil as mentioned, so it should be resting on the firm ground. So to take care of this effective cyclone resistant design, we are incorporating the aerodynamic designs and important reinforced concrete materials and proper anchorage with the foundation, so that we are able to ensure cyclone resistant buildings. So for that, the main structural considerations are stronger roofing systems and use of RCC and steel framings, proper anchorage between the wall and foundation, and the use of flexible joints to absorb the stresses instead of the brittle one, and the load distribution techniques for the main structural integrity. And these are the main features what I have mentioned in the earlier slides, like high strength concrete impact resistant glass as far as the materials are concerned, and the lightweight yet durable roofing materials could be chosen, and use of fiber reinforced polymers may be added to that for the additional strength. And the roofing and cladding systems are concerned, you can go for a sloped, so you can design of the sloped roofs to minimize the wind pressure. And use of interlocking roofing panels is suggested. Only thing is the attachment or the connection should be good. And the water resistant and windproof cladding materials may be used. And as far as the foundation and elevation techniques are concerned, it should be provided in a, you have to provide a deep foundation, and that too in a firm ground for giving full stability. And if it is a soft style, definitely go for a deep foundation. And these are the design procedures, and identify the wind zone first. So you have to calculate the design data first like this: basic wind speed, and based on that risk coefficient, terrain factor and topographic factor should be calculated, and based on that wind velocity to be found, and then you can calculate the design wind pressure. And based on the wind load distribution, based on the building shape, the wind loads, as you have to consider the length, height, width, under the slope and the projections and the area. So based on that, you can distribute the thing. And so structural bracing should be provided to resist the wind forces. So determine the lines of resistance to support roof, wall, and trusses. So essential connections are roof cladding to the purlins with the trusses and rafters, trusses with the walls, walls with the foundations. And as far as the structural design and the resistance measures are concerned, the load combinations you have to choose correctly for the whatever be the worst combination of the load which is taken care of, that should be considered. And you have to, for the preventing the uplift forces on the roofs, the anchorage part, and the connections are mainly important, whether it is a timber building or it is a masonry or it is a RCC connection, then everywhere you have to provide a Pakka anchorage system. And the corrosion resistance materials are to be used for the coastal areas. And also, as it is a wind load, so it is highly dynamic, it is non-linear only, so dynamic stability should be taken care of. And as a last one, the quality of the construction is nothing but it will yield you the safety and durability, so that for which we have to adhere to the Indian standards. So these are the improvements. So what and all we should not do, and what should be, what is preferred. So that is mentioned here, and that is told in the other previous slides also. And here the overhanging to be avoided, no? So otherwise the wind may find a path like this, so it may uplift, and so this may be causing damage to the other part of the building. So these are the recommended size and the longitudinal steel in seismic band in cyclone prone areas. Suppose if the internal length of the wall is 5 meter, is up to say 5, 6, 7, 8. So for those length, there's how the size of the band to be provided. So based on the codal provisions, it is given 10 centimeter wall width, and also the for cyclone prone areas where wind speed is greater than or equal to 47 meter per second, the reinforcement to be provided is 2 bars of 10 mm dia, and this is for lesser than that you can provide 2 bars of 8 mm dia. So like that, for every length of the wall, the rods are given 10, 12, and this is 4 numbers of 10 mm, and if it is 8 meter, 4 numbers of 12 mm dia rod. So like that, for the less than 47 kilometer per second also, wind speed also it is given. And this is for the recommended size of the vertical steel in seismic band in the cyclone prone areas. So for the number of stories, so 1, 2-storied building, and for 3-storied building, how the reinforcement are to be given for the wind speed of greater than or equal to 47 meters per second, or if the wind speed is lesser than 47 meters per second, how we have to give the reinforcement as a band for top floor and for bottom floor and for the middle floor are mentioned here. So based on that, you can provide. Yes. So coming to the conclusion part. So civil engineering challenges in cyclone prone areas are 4 things. One is the infrastructure vulnerability, design constraints, and we have maintenance issues also, and we need to concern with the sustainability. Right? Because everywhere we are nowadays towards passing with our vision itself is vision 2030 is nothing but SDG goals to reach this 17 SDGs. No? So we have to bother about these challenges. So as far as the infrastructure vulnerability is concerned, the poorly constructed buildings and outdated drainage systems are highly susceptible. And as far as the design constraints are concerned, the need for cost effective, but also it should be resistant to cyclone. So that poses a challenge here. So the client may not be having a wish to go for it. And as far as the maintenance part is concerned, the lack of periodic inspections in the government buildings and other areas. And the engineering solutions and future strategies. So for the cyclone resistant buildings, structures, use of RC, flexible foundations, and wind resistant glass in building construction may be a solution. And application of modular housing techniques to facilitate rapid reconstruction in disaster hit areas are possible. Nowadays, we hear within 2 hours, entire house itself is constructed using the prefabricated housing. So such techniques will be of much useful when we go for the retrofit action. And smart urban planning, the elevated roads, intelligent stormwater drainage systems, and also creation of green spaces to absorb excess rainwater. There are a lot of materials are available today. Right? Percolation materials are available, pervious concrete are there. So how we can provide this, how we can provide the provisions to absorb the rainwater in the ground. So that we have to think of. And the zoning regulations to prevent construction in high risk areas and ensure better land use planning. And another part is the retrofitting the old structures. So this is very, very important. Nowadays, this FRP is playing a vital role. GFRP, CFRP, and so many things are the FRP systems are available today. So either in the form of fiber reinforced concrete for attachment or as a wrapping sheet, we can provide that. So that is a novel idea strengthening. And periodic assessments and reinforcement of bridges, dams, and embankments are there. So coming over to the early warning systems, integration of IoT-based monitoring for real-time structural health assessment and implementation of AI-based disaster prediction models for better preparedness. Because nowadays, the machine learning and AI plays a vital role in finding out in giving a solution for this one. So using the drones, we can find out the disaster-prone areas, and we can take images, and also we can code it using the Python programming or so in the machine learning. And using this AI software, AI tools, we can find out the solution as the disaster prediction models. And sustainable coastal barriers. So construction of artificial reefs and mangrove plantations to act as natural storm barriers, engineering sand dunes and other things will be of giving a main effect here. Thank you. So for the questions I am pleasure to answer you.
Thank you so much, ma'am.
Yeah, thank you, madam. Thanks for the opportunity. I'm very happy to answer for a few questions.
Yes, ma'am. Yes, ma'am.
Yes, any questions? Was it interesting or anything? Any suggestions?
Ma'am, I have a doubt,
Participation.
ma'am.
Yeah.
Shall I, ma'am?
Yes.
Yes, ma'am. We are bothering only about the structural damages or defects in the coastal area, cyclonic areas. Ma'am, what
Yes.
about the infrastructural damages, ma'am, because of the roads and dams, roads
Yeah.
and bridges that we are damaging
Yeah.
more than the structural defects, ma'am?
Yeah.
Is there
Definitely.
any precautions that we can do for that, ma'am?
Yeah, that is also possible today. So there are a lot of materials are available. So using that, the road constructions could be changed. See, is nowadays we are using this wet mix macadam, no? So instead of that, we are having the so many advanced materials. So that could be used for laying the roads. So that as a precautionary measure, it will be there. So for bridges also, instead of going for the conventional building material, there are a lot of technically advanced materials are available. So that could be used. I have focused only in the building side, not where I have focused to the infrastructure side.
Thank you, ma'am. Thank you, ma'am.
Ma'am, the one more question asked for participation.
Yeah.
Which ties bars used in earthquake resistance building?
Pardon? Which?
Ties, ma'am. Ties bar used in earthquake resistance
So you
building.
can go for the steel rods or steel patta, steel even material flats can be used. So any kind of thing. Nowadays, FRP wrappings are also given. So many types of materials available. If you go for steel, if you go for steel, choose the steel material, then you can go for the steel rods or the steel flats are available. And nowadays you can go for the polymer based materials also. And that is also possible. Am I answered?
Yes, ma'am. Yes, ma'am. Participation, any questions or any queries? Kindly share your question in chat box.
You're having much scope in this for the research and all. Because novel materials are available today. So how we can apply for the both the tension and the compression, and you can try with the newer materials so that we can come up with a new idea for the cyclone prone areas. Because as far as the Tamil Nadu is concerned, we are having we are more prone to cyclone instead of this earthquake and other things, right? So Chennai is more affected always, right? Every year or almost once in 2 years, it is affecting a lot. It gets affected. Everyone knows about it. And in the Andhra and Odisha and other regions also, all the coastal regions. So for that, how we could strengthen the existing buildings, that is one of the main research area. And also in the areas where we cannot go and suppose after the earthquake, this one disaster, cyclone, the roads are in highly damaged condition. So some potholes are maybe there in every then and there may be having. So for which what we could do is you can send a drone and every 1 kilometer you can take up a picture. So that could be processed in digital signal processing so that you can write a code in machine learning, right? Using Python programming, and you can use the machine learning concept, and using that you can give a solution. So like that also things are there nowadays. No, where the man cannot enter, because in those after this disaster in some of the areas immediately we cannot go, right? In certain situations and in certain villages or in rural areas, you can send the drone and you can take a snap of it, right? And you can take up a research topic itself like that. Any more questions?
Yes, ma'am. We can include the research topic, ma'am. We're providing a new informative research topic also, ma'am. Thank you, ma'am. Ma'am.
Welcome, madam.
Ma'am, there is another question, ma'am.
Yeah.
Chat box, ma'am, from Mr. Saravana Kumar. Any
Yes.
IoT-based mechanism available, ma'am?
Sir, IoT, I am not aware of it, but about this cyclone prone techniques, right? But there are a lot of intelligent mechanisms. IoT things are there. IoT material, Internet of Things, both the construction technology and the construction materials part, right? In both the things we are having. But I am not aware of it. I am not at all used to that. But this AI and drones are playing a very vital role nowadays in civil engineering. Instead of this CSE and IT people, because I am part and parcel of many DC committees, people are using so many things nowadays. AI, ML is playing a vital role there.
Yes, ma'am.
Yeah.
Thank you.
And now the portal provision is also changed for your information. I hope all of you are aware of it. IS 456, right? 2025 is on the way, in which it is the earlier version is having only 114 pages or so. Now this fifth version is about 500 pages, 518 pages.
Okay.
12 loading loads are added. So earlier we used to bother about this only dead load, light load, either only earthquake or wind. So in this two combination, any one of the thing will be dominant, right? But we have to take care of all the things. And in addition to that, this we normally check the system for the design for strength criteria, and we used to check it for the serviceability criteria, in addition to give a little importance to the durability part. But now the new code is giving the importance to 6 criteria. We have to do the design for the strength criteria, and we must check it as a first stage for the serviceability and the durability criteria. They are giving equation for that. And then after this, if both the things are satisfied, then you have to go for the robustness. You have to go for the robustness and integrity. So if these two things are satisfied, then we have to go for the last one as the restorability criteria. So like that, the 6 criteria are there. So RCC become a tough job then nowadays. So we have to solve all the things. We must check all the 5 criteria.
Yes, ma'am. Yes, ma'am.
Yeah. We can have a separate session for IS 456.
Surely, ma'am. Surely, ma'am. Yes, sir. Yes, ma'am.
So it is on the way. I have attended a meeting and also I'm receiving many clarifications. So I'm also giving some suggestions for that revisions. IS
Okay.
456 2025 and draft version is available in the internet. It is available and now the revised version, yeah, it is available, sir. It is in the revised version is not yet come. And then people are asking many clarifications. They are waiting for the clarifications and the solutions to be answered. So for that, they are waiting. Within 2 months or 3 months time, it will be getting released. Even that fifth chapter itself goes for about 200 pages or so, fifth, sixth pages. And we are all this pre-stress content is not having a separate code now. So that will be withdrawn, this 1343. So it is inserted within this IS 456 itself. And also, and as a last unit, the high special contracts is also given some importance as a 12th chapter. So we are having lightweight concrete, high strength concrete. All those things are taken care of in this IS 456. Yeah, if there is no questions.
Thank you, ma'am. Thank you for a valuable, informative session about and beyond the structure also, ma'am. Thank you so much, ma'am. Thank you, ma'am. Karthik, sir.
Sir, any improvements in limit state method? Yes, sir. That's why limit state method is taken care of. The same, you have to design the system for strength criteria and you have to check for the serviceability. But for the serviceability, we are having so many things. All the equations have got changed. And in addition to that serviceability, you have to go for the durability. Durability is a big equation. And also we are having a robustness criteria and restorability criteria, integrity criteria. Integrity and all was not playing role in the earlier version, no. So nowadays for the integrity, a main role is given. The equations are available. So based on that, we have to check that criteria also. Thank you. Thank you, Mr. Saranakumar.
Thank you, ma'am.
Thank
Shall we
you.
conclude the session, ma'am?
Yes, madam.
Karthik, sir.
Yes, ma'am. Yes, ma'am. I extend my heartfelt gratitude to our esteemed chief guest, Dr. Tenmali, Professor and Head, Department of Civil Engineering, Government College of Technology, Coimbatore, for gracing this session with her presence. Her valuable insights on construction future of cyclone-resistant buildings have provided us with a deeper understanding of a resilient infrastructure and a crucial role of civil engineering in mitigating of cyclone impacts. Thank you, ma'am. Your time, expertise, and inspiring words. Thanks a lot. A big thank you, all of the attendees, for your interesting participation and engagement. See you all on tomorrow. Thank you. Have a great
Thank
day.
you for patient hearing in this late night, 9, 10 now.
Thank you, ma'am. Thank you once again.
Yeah,
Thank you so
last
much,
out.
ma'am.
Yes. Yes, sir. You
Sir,
can.
great.
I think one of the person is asking something. Yes.
Arunakumar is asking about the fire or thermal load included, ma'am, included in the IS 456 or not?
Fire or thermal load. So
Fire or
that's
thermal.
what so I have read about some halfway, sir. I have not
Yes,
at all come to that end because I'm having some 400, 500 slides about in IS 456 2025. I have not read fully. Last week only I just downloaded the material. So for just sending clarifications to the from where I am getting the I have got the clarifications. So for that only I am started reading that. Only half the part I read. I have not come across this fire and thermal load. I have to see.
Thank you, ma'am. Thank you for your patience. Thank you for your support, ma'am.
Once again, thank you so much, ma'am. Last minute, I will connect and giving a wonderful session, ma'am. Once again, thank you so much, ma'am.
Thank you. Thank you. Thank you, madam. Thanks for the opportunity given to me.
Yes, ma'am.
Thank
Yes,
you.
ma'am. Yes, ma'am.
Thank you, ma'am.
Okay, madam. I shall take leave, ma'am.
Yes, ma'am. Yes, ma'am.
Thank you.